Engineering, of Mechanical Engineering, emerging technologies in optimizing renewable energy systems with skills and storage solutions. This we have been successfully completed 3 days, and our active participation is more appreciated. And the lectures delivered so far is delivered with zeal and enthusiasm. We'll continue our 4th day FDP. I am welcoming faculty, research scholars willing to participate in this FDP, various parts of the country, and I welcome you all for this 6th day for the session 7. We have designed 2 sessions. First is by Professor Pramod Kumar. Second session by Professor Dr. G Anil Kumar. Professor Pramod Kumar Singh is a professor of physics from the Sharda University, Noida, Uttar Pradesh, India. Now, in our midst, our colleague, Assistant Professor Mechanical Engineering, Kakinada, Dr. Prasad. I would request him to today's guest speaker of the session 7 of the day, and welcoming him to take up the session. Thank you, Madhu.
Thank you, sir. Good evening, sir.
Madhu.
Yes, sir. Thank you, sir. I guess of this 6 day, me the opportunity to introduce Professor Pramod Kumar. Good evening, sir. Professor Pramod Kumar Singh, sir, as Dilip sir introduced, he is presently working as head in the Department of Physics and Environment at Sharda University, Noida. So, from Banaras Hindu University. He's been in teaching and research for many journals and in various conferences and all. He has awarded the world's top 2% scientist by Stanford University. He has obtained his postdoc in from South Korea. Has been abroad for several years. Currently associated journals as the editor member. He, apart from teaching, sir has guided many bachelor's and master students. Recently, several students have registered under the SAR guidance for study and all. SAR is presently working in areas like polymer light, materials for licensed types for and SAR is presently having these projects mostly working under these areas. Material science, which is a project funded by Government of India. Thank you, sir. With this small introduction, I will like to hand over the session to Dr. Pramod Kumar Singh, sir. Thank you, sir.
Thank you very much, Dr. Madhu, for introducing our guest speaker, distinguished. So I would now request Professor Pramod Kumar Singh, sir, to take up the session. Thank you very much.
Thank you, Dilip, for this. Yes. So everything is audible?
Yeah, sir. Shall I share the screen, sir?
I think it's better you share you say screen, and then time to time I am going to introduce myself and my students.
Sure, sir.
Thank you for nice introduction. And I think it's a nice introduction. Through internet or maybe artificial intelligence, I am able to deliver my lecture at least online. Yeah, after you can say heavy load from my university and other, we must thank, you can say everybody have to thank our students nowadays, because without that
Yes, sir.
it is not possible to maybe faced by Dilip or Madhu or any other person.
Yes, sir.
Yes, sir. Yes, sir. Thank you.
So thank you for inviting me, particularly. And as a teacher, as a researcher, I can say that I am blessed with this material. Long years back when I did my PhD in, you can say, from Banaras Hindu University, very well known in North India, you can say, in 2001. So before going to introduce this material, I think let me introduce how I can connect these materials, my audience, my colleague, researcher, which is online. So when I did my PhD in that time, I am talking about year 2001 when I got my PhD degree. So my professor, means my PhD supervisor, is a well-renowned professor in one area of material science. It is known as solid state ionics. Solid state ionics, you can say, kind of material science emerging field where we are dealing with ionic motion by ions. So of time, many people are working in material science, but they do not have that where they have possibility to explore their own things. And I believe, because I spent, you can see, more than 20 years in this research area, everybody have to know about his or her own, because you, without taking another one hand, you cannot clap. So collaboration and cooperation is very much important, and particularly that one I am blessed by one of my late PhD supervisor, Professor Chandra, who introduced me in this area. So I got this, say, my PhD degree in polymer electrolyte, not in material science, in electrolyte from Banaras Hindu University in year 2001. And then I am always taking dream, like every colleagues have taken to get a good job, but I am always taking to get a not good job, maybe postdoctoral fellowship. So my earlier, I think he has already given something about battery. His name is Dr. Dipolu. He is my close friend. Also, as a laboratory point of view, you can my junior. So we are coming in one circle of known materials class that is known as solid state ionics. And polymer electronics, whenever I am going to ask with my PhD supervisor, he always say me that you write a good paper. So believe me that I do not understand what is his own meaning to say this word, but now I understand that if you are a good teacher, although you are knowing things in material science or particularly specific area, but you can say your own intuition, you are supporting something other than your academic career. This research is very necessary. So I am heading two departments in Sharda University, and as Madhu already told, I got some doctoral experience from, you can say, South Korea, Turkey, Japan, where I learn how I can use polymer. From each country visit, I learn something. I am going to deliver, it means just delivering 2 hours is not task, but just to, you can say, mapped well with your lectures thing. So I am just connecting you with my earlier story, and then directly coming to own choose particularly delivering this kind of thing. So that time it's in university, whenever my professor is going to ask, what is new? So that on basis of that one, you should go and finish your PhD work. I am always in dilemma because solid state is a vast field where people are dealing with polymer material, composite, nano composite material, okay, ceramic fillers, nano ceramic fillers, many more material. So I am approaching to my professor, he always see me. First, you come with solution. So as a PhD scholar, you can understand my situation. It's very tough. Whenever my professor is asking, I do not have clear idea. By God gift and by clear motivation, now I got that where I want to work. And that area is known as polymer electrolyte. So whenever I am doing, means you can say in PhD journal, almost in my all paper, you can find that in conclusion, right, okay, this material have very good ionic conductivity, maybe order of 10 power minus 4 minus 5 Siemens percent, and these material have future application in electrochemical device. So when I got my first you can say postdoctoral fellowship in South Korea, I was very excited because before that one I never take a plane visit, aeroplane. So first one is very curious that how people are going to ride in aeroplane. Second one thing, I am always taking dream because I am belonging from a middle class family. You can say my father inter college principal and a teacher in mathematics. So that one is my first visit. I want to share something to you. So when I am going to plan to catch that flight, my professor that day, last day, he introduced me a nice way that this one is the journey where you are going to learn something. Before that one, he can teach many things, but that last word, that please go abroad and learn something new. So many things in my mind. I have taken my aeroplane, and you can say in year 2005, I got postdoctoral fellowship, and I took a, you can say, aeroplane to directly South Korea in Sogang University, where Dr. Anji Polu Reddy laterally do her own, you can say, postdoctoral work. Both are came from same laboratory. You can see in interview, I am Dr. Anji Reddy. So when I reached Korea, my professor did not tell me anything during 6 months. Again, going to very upset. I came to learn something. Professor did not tell me. Every day he's just sitting on that one, and once a week he's taking some meat and then simply go outside. But after puzzled, and then I directly reached to my, you can say, Korean professor. And I tell, I do not came here to just see some Korean movie. Please tell me what I have to do. Simply one sentence that now you came for postdoctoral fellowship. So each come with your own idea. If you do not have idea, then I think I am just wasting my time to get a good postdoctoral. So that day I am thinking, real thing, what I should go to out in Professor Hugh. And that time I realized that what sir told, that please concentrate on your paper conclusion part. That one give me a path where I that this much ionic conductivity always helpful to make a good electrochemical devices. That day I have decided that of course in this laboratory, Professor Ree laboratory, there multiple battery applications, you can say, are supercapacitor, solar cell, electrochemical, other application like supercapacitor and other thing. And I contribute a lot, means 4 years I spent in Professor Ree laboratory. So where I learned the actual meaning that how I can apply this part in dye-sensitized solar cell. Another one area of, you can see, polymer electrolyte is making supercapacitor. So something topic which I am choosing for today talk, you can say it's related with environmental safe materials for electrochemical application. So basically I am dealing only with material science, and application part is, you can say, something different, which anybody can find me easily through internet or through, you can say, Google or Google Scholar or everything. Pramod K Singh, and you can maybe put comma and then put supercapacitor. You can find my own work in this area. So I spent 20 years in this area, and today about, you can say, material kind of from basic things. Basic things means anywhere or any new work, if you do not know basic work, I think it's always a challenging task. Know where you are going to contribute. And if you know something basic, then you can maybe, you can say, researchers who is working already in this area. So polymer electrolyte is my backbone. I think before going to just enter in polymer electrolyte, I tell something about material science, particularly material science is first. I am going to request Dilip to come on my next slide, please. Yeah. So this slide shows a very basic things which I always tell to my student. Try to understand how much broad this material science is. So materials you can broadly classify in various ways. I think on basis of their states, means how its state is going to exist in nature, you can differentiate. Already it's in literature that solid, liquid, gas. So first of all, whenever I am going to talk in front of you, it is not related with liquid and gas. I am talking about materials. Solid means solid, not in liquid phase or gaseous phase. So next slide, please. Yeah. I think many people already, you can see every day you are seeing or maybe listening to many lectures related to nanomaterials, metamaterials, micromaterial. But if you understand actual meaning of, you can say, metamaterials, means I am talking about macromolecules and micromolecules. There are another kind of thing. So you can say molecule point of view, I am talking about macromolecules and nanomolecules. So if you are going to introduce before any audience without knowing what is the importance of nano, there is nothing you can say about nanomaterial. So everybody is now running nowadays. You can say earlier people are already running, but nowadays everybody is talking only about nanomaterials. But without knowing that what kind of behavior the same material is giving when size is bigger, you cannot predict anything. So I think device point of view today, material engineering are, since you all are faculty of mechanical engineering, so people are always devoted towards their own area. Means mechanical people are always thinking about mechanical stability, young models, and other things. But if you try to means I am going to convince you that why you are going to learn some other kind of area. Apart from this mechanical study, if you have something idea about another part, means I am talking about electrical property or structural property, and if you correlate it with your mechanical property, it's very good. Otherwise, if you think that you are perfect, no one is 100% perfect according to, you can say, physicist rule. Even Carnot engine, we have already believed that it is not, never ever any engine can be more performance than 100%. So everybody has some defect. And then this defect is playing a very dominant role. So time by time, I am going to tell something about. So next slide, please. So whenever I am teaching, basically I am heading two departments. So this, you can say, university give me opportunity that I am taking only one lecture. And other things, other loads are managed by, you can say, official work. So I am taking only, you can say, material science classes in MSc final year student. Particularly, I have designed for my MSc final year student. And whenever I am going to teach, I am trying to understand, every student will try to understand what is the nature of materials. If you love with materials, if you know something about material, then you maybe enjoy with research or teaching, otherwise no. So this slide I have taken from a very good book. So anybody, I think most of, since you all are mechanical engineers, so everybody know about this book. So this book, chapter 1, I suggest everyone to read. Not right now, you can say, I have PDF copy. You all have PDF copy. If you do not have, you can ask me. I can share anyone to you. So this slide I have taken from this book. I love this book, particularly with two reasons. Whenever I am going to teach any class, I think this book already give in chapter 1 too many answers. If you are going to introduce mechanical property, if you are going to deal with electrical property, if you are going to deal with structural property, if you know something about material, that how it is going to behave, where it is going to be useful, then you can define your research area. So, to this book, I have already taken this picture say that according to strength, because you all are mechanical people. So I just, you can prepare this slide particularly for you. So on basis of divide a whole category of materials area. So one area where it's already written engineering, then engineering ceramics, then engineering alloy, then engineering porous ceramics, then engineering elastomers, polymer foams. So you can see a variety of materials exist in nature. And strength people have already measured. One suggestion is that if you are going to work with any material, try to, if you are going to use your own materials, people have already given in literature and everywhere how much strength it is going to bear with. So if you want a tough material, people have already classified. And in this book, they clearly mentioned that if you are working in engineering ceramics, go up to 10,000, you can say megapascal. And I am working. You can see here in engineering polymer, one you can say lines. So I know resistance is little bit, means you can say many more lower order of magnitude in comparison to engineering ceramics. So I want to say on basis of this slide that every material have different strength. And if you are going to develop a device, you know that how much strength you know, how much conductivity you know, how much mechanical strength you needed, how much you can say thermal ability you needed. Then you can material and you can play a different role. Next one. I think I like or maybe you teach using these slides. Anybody can, that one is my own, not my own property. Anybody can share and teach to a student. It's a already old setup. It's retired from you. Now you see, in each you can say cross-sectional view with different color. Everywhere, HRSI, RSI, FRSI, everybody. Kind of any aeroplane. Aeroplane, you already know. Nose point, you know, maybe need another kind of material, which is very tough. Because plane is taking long height and very, you can see speed and other things more. You need a very strong material. Apart from that one, if you are going to, you can see working for aeroplane area, I think I am talking an area, you name how much with pressure, how much temperature is reasonably going to generate. The people where we are sitting in aeroplane, It's roughly needed temperature 300 to 400. If you are maintaining a height, there are pressures, so ultimately temperature almost settled. According to that, taking their own heights or their own speed. So it's already clear, very clear in this one that nose portion, which is going up to, you can say, 400 to 1000 degrees. The people where we are sitting or we are going to sit in, we need temperature in between, you can say, 300 to 400 degrees centigrade. Basis of that one, people have already designed a tailor-made materials. So tailor-made material, already tailor means it's specifically whenever you can say your clothes is going to tear, you go and tailor. What tailor is doing? He is taking another cloth and going to sew, and you can find a very good clothes. So same kind of material, these are tailor-made material. You can say in mechanical side, you can say it's alloy materials. So on basis of that one, you can reasonably choose whatever material you are going to use with. Next slide, please. Yeah, so whatever I shown in, you can say earlier slide, it's already, its full form is given in this table. Means FRSI, failed reusable surface insulating materials. It's already minimum operating temperature, maximum. People have already discovered. So nothing new. Only your things is that whatever or whichever area you are going to work, you know their own strength. So ultimately, I am coming in another kind of materials which is known as carbon-based material, because most of people nowadays working with carbon-based material because it's carbon nanocomposite, carbon, many allotropes and other things I am going to tell you in coming slides. So you can see FRSI, AFRSI, LRSI, RCC, which is always discovered for a nose point of, you can say, any aeroplane. Design nanocomposite, RCC means reinforced carbon-based material. So it's a kind of alloy, it's a kind of, you can say, tailor-made material, it's kind of very tough carbon-based material. People have already discovered too many things, but never fight with, you can say, nature. Otherwise, nature is also fight with you. Now we can say our one of well-known Indian astronauts is fighting with the space shuttle nowadays. You already know her name. And it's everything is gone when its nose portion is going to felt down. So people are discovered. It means that we are not discovering a new material day by day, but you can just expect from its merit. Demerit, many things are decided not by man-made, you can say, when it's going to be real practice in space or maybe in your ground state. So next one slide, please. Yeah. So I want to say that you can see in middle portion I have written only one word. You can say sentence. Properties of material are size dependent. It's already well known. Bigger materials means bigger particle size have different property, and same materials. If you are able to discover nanomaterials, its property is totally different. And material science and material scientist, you can say, always playing with each other. Where you can say you can make a very good material, you can make a very bad material. Maybe sometimes it's going to be achieve a very good material, sometimes it's going to be failure. And it is only on the basis of this particular one sentence that properties of material is size dependent. And materials, or you can say other carbon enforced materials, people are always playing a very good role when size going to comes around nano size. Here. Nano means 10 power minus 9. Next one, please. Yes. So now from nanomaterial, you can say I am talking about materials, nanomaterials, bigger material, nanomaterial, now nanotechnology and nanomaterials. So technology which is developed by, you can say, nanomaterial based, where any one component, you can say if we are talking about three-dimensional nanomaterials, where we are talking about length, breadth or height. So be careful. Nano doesn't mean that everything is in nano size. people are always in dilemma. And whenever you are going to attend many conferences, you can see in my background. Recently, I have organized one international conference with backdrop. It's already shown in my laptop, you can say backdrop, where we have discussed. So try to learn through conferences, through, you can say, webinar, through FDP, and try to ask some questions also. It's very good. Otherwise, it's looking like that I am going to deal something. If anybody is not curious, so it means only two things. You already know. Either you could not understand anything, or maybe I am delivering whatever you can just listening in audio modes. That's all. So I want to say that whenever you are going to develop any device, and believe me, if your either length or height or breadth, any one dimension, any nanomaterials, you can say it's in nanotechnology. And nanomaterials particularly governed by whenever you are going to make a size smaller, and many more smaller. So next, please. Yeah, next. Yeah, I think it's a very common things. Everybody know about nano size. Nano size means 1 billionth of something. 10 power minus 9 is nano. So when meter scale, anybody can decide that one. So I am not going to deal anything because I believe that it's for my colleagues. So everybody know. And this one, yeah, next one, please. Yeah. See, it's already written everything that an atom is one of the basic unit of matter. Every physicist know it. And everything around us is made of atoms. So physicists believe that we made by atoms. Everywhere, my organs, my everything, it's made by atom. And an atom in a million's time, it's already, you can say, people have already measured its diameter, and it's always came in nanometers. So it's already mentioned that your maybe hair, your maybe other kind of tissue, how much its length, breadth, or height. Next one, please. Yeah. So 1 billionth of a meter is 1 nanometer. 1 nanometer is approximately, you can say, 6 carbon atom, because chemistry people know carbon, everything people have already measured. Diameter of normal human hair, not, you can say, my hair, because my hair is not little bit thin, maybe thicker hair. Thicker human hair is 60,000 nanometer. And DNA, which is inbuilt, or you can say our tissue culture and biology people know, DNA, RNA, ribonucleic acid, ribonucleic, DNA molecule 2 to 15 nanometer. And physicists always behave that if you comes around Bohr atom, which is known as a hydrogen atom, it's already diameter, already defined 0.1 nanometer. So I believe if you are deal with nanometer, you must know about limit. Limit means from how much nanometer and till end of nanomaterial. Please. I think this one is the same things which I have already discussed, so I am not going to do many things on this slide. Next. Yeah. If you are going to be a good researcher, I always say, things around you, industrial innovation, maybe higher, you can say, third, anybody say, go to industry, find something to help you in your own research or any other things. Have, you can say, circle wise. Circle wise means in chemistry people always that for a good stable reaction, oxidation and reduction balanced. Physicist, we say that every if you are reverse motion is always possibility. So try to balance it. So many social issues around you, many industrial innovations or materials around you. Human resources is always a very good career. And if you are going to deal with all kind of things, means I am not talking that I already told you that if you know something better than any researcher in subject, it doesn't mean that you are 100% perfect. No one is 100% perfect. Some portion you have to deal with research, some portion you have to deal with your own science or whatever knowledge you have to student. National and international cooperation is also very important. Not a good collaborator. Now you see, I am one example. I don't know that because I'm sitting in our side and this happening. So this one is the one platform where I know one of my Anji Reddy Polo. He introduced me with this nice guy, Dilip. I can tell something about this nanomaterial, particularly a carbon-based material. Next one. Yeah, so these two gentlemen, I think whenever you are going to teach, everybody say that these are the, you can say, two renowned scientists which discover something about nano. Is tell, you can say another one approach, another one. So one tell me is going to tell that have a bulky material going to crush it by then by machine and other things. That one is known as, you can say, one top down approach. Get a very small, that is nanometer. So that approach is known as top down. Other one, he is introducing another one kind of, you can say, your body culture. Body culture means I'm talking about tissue culture. Biological people where too many tissues going to join together and make a 1 nanometer material. Or you can say your DNA structure or RNA. So DNA RNA structure, it's a bottom-up approach, and if you put by hammer bigger molecules into a nanometer, known as top-down. So these two gentlemen are always thankful. Say top-down and bottom-up approach for nanotechnology. One. Yeah, so everybody want, you can say many, I always say, everybody want a lighter thing. I want that in my pocket, such a big size of, say, my cell phone is there. So I want a lighter. Apart from that one, I also want that its pixel size is too much good. Maybe its capacity is also much higher. So now everybody want a lighter material. Lighter means smaller in size. So people not thinking about a bigger materials in any kind of development of technology. So thinking goes down. So in area, like I can already mention in red colors, electric, solar cell, coating, life science, and you need to material cheaper because it's reasonably, everybody can afford that one, and make smaller so that it can easily put in your own pocket or maybe not very heavy. Next one. So as a physicist, I can say that phenomena which play a dominant role. If you know the quantum effect, this is known as quantum size effect. Anybody can, it's not a bulky size. That right hand side, so if anybody want to define confinement or quantum size effect, first he should be understand that he is working with the conducting materials. This phenomena only happen in conducting materials. This happened in ceramic materials or insulating type of material. It's dominant in play. And conducting material, I'm talking about semiconducting materials. As physicist, you can say layman, spongy kind of structure. It means two slice. So upper side, it's a known action band and valence band. So everything happen between, you can say, valence band to conduction. And you can say in one type of, you can say any molecule state more than millions of state there. State find a semiconducting material that there is a band. not BOND. Totally. So band structure model say that every semiconducting material have two states. Lower state is known as valence band. State is known as conduction band. So what happens in bulk size of material in between gap of these two band gap? That one is known as Fermi band gap. That one is known as band gap. This one is very small because it's a solid material. Solid, I am talking about solid semiconducting material. So you can say up lower size of this one, the band gap is very small. And that one phenomena is known as quantum confinement. So lesser band gap, you can say a very good bulk material for that one. If you are going to deal with nanomaterials, compare with this bulk material, this one state means I am talking about valence band. Now you see the downwards band, downwards slide, it may be cut into many small pieces. That one is known as energy states. So in nanomaterials, this you can say valence band is also confinement. So now you can see a one kind of thicker braid. So in bulk material, I always say that 2 or 3 slice. And if you are treating the nanomaterials, you go maybe very thin slice of that one, this band gap is going to increase. So slightly you can see here energy gap between this valence band and conduction band going to uprise. So when it's going to higher side, people always believe that it is moving, my particle size is moving towards nanomaterial. And this phenomena is known as quantum confinement because it is happened only in nanomaterial, not in bigger materials. So this quantum confinement, or you can say quantum size effect, always happened in nanomaterials. And now, according to new, you can say definition earlier, be careful when you are going to teach with nanomaterials. Try to understand how much particle size or quantum confinement or any dimension already defined. And people already defined about the other kinds, and that one, I already told you that they have defined a separate unit of defining this nanomaterial. And that international body is known as IUPAC. Chemistry people know. That body is year-wise, after this kind of discovery, discover that how much quantum, how much size we can treat this material as a nanomaterial. So earlier people believe that 1 to 1000 nanometer is nanomaterials, but you can say researcher already adopted in theory by IPAC that 1 to 100 nanomaterial size in each case, I am talking about length or height, is treated it as a nanomaterial. So whenever you are going to attend any conference or you can making one material, be careful that if your material size, many dimension is not in between 1 to 100 nanometer, you never say that it is a nanomaterial. So many conferences, I got this point and I saw many people are just fighting with, you can say, old researchers. So big fight between old researcher and new researcher that how you can define a nanomaterial. If your particle size is nearby, you can say 500 nanometer, people can say it's a nanomaterial. But if you are updated with research, now IUPAC clearly says that any one of dimension, it comes into 1 to 100 nanometer, then you can treat. Otherwise, it's not a, you can say nanomaterial. So I think nano size effect, it's, you can see by visually color, conductivity, crystal shape, magnetism, melting points, reactivity, many things. Some of example I am going to see in front of all of you. I think next one slide, please. Dilip. Next slide, yeah. So this one everybody knows. Gold, I think any you can say male or female love with that one. Bulk gold, everybody knows its color. Its everything is defined. You can see here, gold, bulk gold, melting point is nearly more than 1000 degrees centigrade. Color is golden. And if you are going to deal this gold, and it's already, you can say structure and everything is already mentioned. You can't say anything. It's, you can say shape, size and everything. And if you are able to make this nanometer, this material into very smaller size, I am talking about 1 nanometer gold particle, you can see its melting point is totally different. It's also totally different, coming to brownish side. Now, if you are still not satisfied, and if you are dealing with a, you can say 20 nanometer gold part, its color is totally different than golden. You can find a red color nanomaterials, and it's a different application. Its structure is also different. So bulk gold is different structure. You can say 20 nanometer gold particle is face-centered cubic structure. And if you are able to, you can say, synthesize 100 nanometer gold particle, its total structure is going to change from FCC to icohedral. So everything is going to disturb. You can say its melting point is going to change, its structure is going to change, and you already know that each one according to their own application, everything is going to change. Means application of this gold, bulk gold, is totally different. We are making in ornament. Now this 20 nanometer gold and 100 nanometer is already well known for medicine. I think South people are very rich in that one. And that science, you already know, that medical knowledge, Ayurveda. In Ayurveda, there is one very famous medicine, which is known as Swarna Bhasm. You can say in Hindi. Swarna Bhasm is nothing. It's a gold nanoparticle. It has different application. It is killing bacteria. It is killing many diseases, bacteria. That's why if you are able to, you can say, synthesize nano gold particle, you can maybe apply same things apart from, you can say, ornament to Ayurveda or medical science. Next one, please. Yeah, so nano sizing effect always change chemistry. You can say it's going to change everything, reactivity and other things. CNR Rao, it's a very renowned professor, very close to South people. I think North people also love with that one. And we love with this chemist because he contributed a lot of papers in this nanosize area, where you can see if you have a bigger particle, it's totally reactivity and bonding is totally different. And if you have a smaller nanoparticle, you can maybe attach too many functional group apart from the CO group. So it's case is going. Next one. One thing measure by, say, is BB. I'm talking about not bottom size, this one, maybe that one, which is given inside that one. You can see there is size change and your peak is going to change. What does it mean? According to particle size change, your lattice parameters, HKL value, everything is going to change. Your material is behaving from one state to another state. Its change is going to totally complete from one state to another solid, another type of material to base. If you can remember my earlier one slide where I have written every size dependent property. And if you are going to size a tailor-made material, if you know size, tailor, you can develop a very good nanomaterial. Next one, please. Yeah, so it is also going to change. I already told you parameters going to change. Fusion, I have to say it within enthalpy. So heat of fusion and heat of fusion, two other things. Both things are going to change when you play with size-dependent phenomena. Next one. Yeah, so magnetic properties are also going to change. Next, please. Yeah, coming to another one, spectroscopy same material, if I am taking a spectra, starting from 6 nanometer to nanometer, this particular peaks is split into many phases. What does it mean? It means same may be behaving in different type. So its structure is going to change, everybody is going to change. Next one. Yeah, so now I think these are I'm going to tell something about a very good how you can front up your student that their nanotechnology is going to play an important role. So just try to understand, say, teacher, if you are deliver something to student, first you clear, very clear point of view or very clear your vision so that student can understand what kind of. So this one maybe you can take a very good example whenever I am going to teach my student. So there is a beautiful garden where you can say many roses are there and you never see. So start this journey, you can say, with a little bit related to material science. Now I am coming with very closer to make this session very lighter. So this one is the garden where one bee is sitting, and right I am putting one scale. You can say slightly I am moving this scale. It means I am going to zoom it. So now I am going to start from material science. I am going to introduce in a one area, specialized area of characterization, and that one is known as microscopy. You want to see any picture magnified view. So now next slide, please. Yeah. So I think it's a, you can say magnified view. You can see my slide, pointer slide, maybe that arrow side is now little bit shifted from 0 to 1. What does it means? If it is in meter scale, now I am talking about a 10 centimeter scale. So from 0 to 1, its distance is 10 centimeter. And in this magnifying view, I am watching this, you can say, beautiful flower or garden. So whatever happened, I think in my, I'm going to child would, like we have taken a circular glass and put in circular lens, not circular lens, and we placed in front of, we are going in field and we are collecting sunlight, and nearby that one, or you can say bottom side of putting a one glass, maybe one paper where sunlight is collected and automatically it's focused and one ray is going to burn that one side and you feel very happy. So that one is peculiar type of things which I already played. I already played in, you can say, your earlier generation. That one deal with your student, you find it relevant when they are enjoying with your own class. So this simply signifying view of one particular selected area of this garden, and where you can say on one leaf there which is sitting. Clearly you can say, I can see, say, glass. Maybe you are also able to see it. Next one slide. Yeah, now I am going to slightly move. So now you can see my pointer is going from 0. It means now I am moving. Now I am zooming everything to see where this fly is. So very clearly in 1 centimeter scale, it means 0 to 2 is considered as 1 centimeter. When I focused this much, you can say this beautiful garden. Now you can this fly with 2 eyes, and there are some needles on his mouth, and maybe wings are also clearly seen. Next. Yeah. So now I am again moving. Now you can see, able to see 1 millimeter scale. Within 0 to, you can say 3, 1 millimeter. So further zooming, say more, able to see its fly eyes. How it is going to connect with nanotechnology? I am going. That's why I am moving directly to my next slide. Next slide, please. Yeah. Talking about, you can say, bigger particle, not coming to nano, say just in between millimeter and nanometer. That one is known as micrometer, 10 per. So now I am slightly moving my scale, another one. And it's now comes from 0 to 400 meter. These 100 micrometer, you can very easily see. And each packet, I am talking about, it's made by packets, too many packets, like a soccer ball. I can show, I can say, I magnifying view. So each packet is a small lens and with light sensitive set. Maybe you can go to bigger size, then you can see very easily that one. The hexagonal pattern of red pigment gives the eyes its color. Means any fly color is red, blue, green, any colors. It means it is the eyes, means that fly is made by any packet. In between one, you can say packet, there is one lens which is very sensitive. That one, the pigment, that one, and the colors, its eyes is looking like. So you can say first one is the cell, and then inside that one there is a pigment. Next slide, please. Yeah. So this slide I love, because now you are not satisfied with the earlier slide. Now you move little bit, so it's coming into 10 micrometer size. 10 micrometer size, same packets, you can see it's showing very good picture. I already told you in my earlier slide, there is a, in between these packets, there is a lens. This lens is very clearly visible here. And each fly, you remember, whenever you are entering in any garden or maybe in your own room, there is flies. Of course, any flies. When they can just see your vibration, they can take a fly and they can go away from your own foot. Who is responsible for that one? This sensor is responsible for that one, is nano sensor. So nature already give you too many things, but you try to understand how nature has given you a nanotechnology. Many more examples. This one is only one, and it's already on internet. Anybody can download it. So you can see very easily 10 micrometers means now I am magnifying many more. And now anybody can say it's a, people have believed, people nowadays people have make a very good instrument that is known as scanning electron microscopy. So microscopy area on basis of their own, you can say, their magnification and other things, you can define a characterization tool which is known as simple microscopy, then scanning electron microscopy, and then transmission electron microscopy. So if you are going to deal with, you can say, 10 micrometer size, then you need a better resolution, you can say, equipment, and that equipment known as SEM. So nowadays everybody knows SEM, TEM, and maybe many more, AFM and other things. But try to understand why SEM is necessary, how much it's costly, why it is costly. The reason is this one. You want to see a lens embedded inside a fly's eyes and its size in nanometer. Then you need an instrument which can magnify so that you can easily visible to everyone. That's why these instrument cost is according to base their magnification, its cost is going to vary. So using SEM, you can very easily see these kind of fly eyes, you can say sensory elements. So that one is known as nano sensors. And this nano sensor is not provided by yourself or not man-made. It's always remember it's God-made. And nature already give you too many nanomaterials. You need to smell, you need to think, you maybe need to identify it either by visually or characterization tools, or maybe your own, you can say, guess or something doing research in that one. Next one, please. Now really I am coming into nanomaterials. So now I am again zooming it in 1 micrometer. 1 micrometer means I am moving towards, you can say, nanomaterial. Now you can see from 0 to 6, if this scale is 1 micrometer, you can easily put this 0 to 6 in this nanosensory, you can say, element. You can find its thickness. Roughly thickness is, you can say, 1.5 micrometer. I am talking not about length, I am talking about breadth. So its breadth is nearly, you can say, 2 micrometer or 1.8 micrometer. So if you have these kind of resolution tools, then you can understand how much thickness, how much its length, how much its breadth. Next one. Yeah. So now I am coming to nanomaterials particularly, which I want to talk. So this one is scale, if you can, so from 0 to 7, now it's treated as 100 nanometer. Now same kind of structure which I shown you in earlier slide. Now you see how much structure it's looking like. So yeah. So next one, please. Yeah. So now if you correlate these two pictures, now you easily understand that each maybe sensory elements make by too many slides types of structures, which is clearly seen here. I already told you that if you are going in semiconducting material, this one is band structure, valence band, conduction band. And now if you are dealing with nanomaterial, this valence band is going to slice in many ways. So this one is the same example related to it. So now you can say one band structure, there are too many slides. So this one is known as sensory element, which is made by nanomaterial. Nanomaterial means now you can say length, you can maybe say it's in micrometer, but what about its particular thickness of each one label? It's really nanomaterial. From 0 to 7, it's 100 nanometer. I can say that it's made by, the sensory element can be made by, you can say, more than 1,000 nanomaterials. Fiber, or maybe many different way to say that one. Nano fibers, you can say. And each one have roughly thickness between 1 nanometer to 15, you can say 15 nanometer, and they all are stacked. They are layered, and in between that one there is a pigment which give you color. So science or nature already play a vital role. And next one, please. Yeah, and then I am going to conclude my this slide, at least you can say nanotechnology. So this one is the picture where now biology players always love with this slide. This one is one, you can say, DNA structure, deoxyribonucleic acid. So this one is our, you can say, our whole, you can say, tissue and other things. You can say it's already related with your other kind of things, means your tissue culture, our shape, size, and everything. So each one, you can say, it's a helical structure, and it's made by a kind of structure where I can say ATGS or TGGS, or people have already, and that one is known as genetic syndrome or genetic pattern, which I am not going to deal. I want to say that if you can see, just concentrate about 0 to 8 scale. This one, you can say length is 10 nanometer, and you can put the same scale into this DNA structure, where you can find that it's made by either 1 nanometer or 2 nanometer or 7 nanometers. So real, if you come from fly's eyes, which I already shown. Next one, please. Yeah. Then another one, next one, please. I think I am going to conclude this slide. Yeah. So now I have started from, you can say, natural fly. and I come in nanomaterials. You can say step by step, I have already told you that why its eyes is looking like yellow or blue or something like color. It's due to pigment. This particularly, you can say RNA, DNA, genome structures or maybe particularly pattern define you that actual nanomaterial which is already embedded inside this fly's eyes, and the sensor material particularly which is in nanomaterial size, which sense very fast. So if you have developed a nanomaterials, I already told you by example of one Professor C.N. Rao slides, that your sensory kind of things, your sensing things is going to much more higher in comparison to bulk material. Very fast, you can say. So this one is the true example given by, you can say, human beings. Our nature already provide you too many things. Coming to next one slide. Yeah, so I told you that characterization tools based on this microscopy I've already discovered. On basis of these kind of experimental tools, you can say you can characterize material, and these machines, according to their magnification, you can say SEM, TEM, X-ray, FM, BET, another kind of measurement, which is always play a dominant role in nanomaterials, means pore volume, pore size, everything. People have discovered these kind of characterization tools. According to their magnification, their cost is going to vary. Next one, please. Yeah, these are the some experimental tool, you can say, just a pictorial presentation. Next one. This one is also X-ray. Next. Yeah. Now I think I have already played 1 hour in this. You can say something about nanomaterial. Now I am directly coming to my whatever topic I have chosen, particularly to teach all of you, or maybe going to give something related to material science. So now I am directly enter into one of the particular area of material science where I am embedded with, apart from polymer electrolyte. So polymer electrolyte is always my backbone. And polymer material, I'm working in polymer material, maybe different kind. On basis, I have already told you that on basis of each material state or molecule state, you can define material into 3 states. Similar kind of things. Polymer may be defined in many ways. Similarly, carbon is also exist in many types of carbon. You are dealing with carbon conducting, you are dealing with, you can say, insulating carbon, semiconducting carbon, many more. So now second journey, I want to play with you on one beautiful material, I can say, which is very rigid. Carbon-based material never play a very friendship with too many materials, you can say, exist in nature. So they are rigid, but you can easily, this one is the only one material which exists in 3 forms. You never find any material which can exist in different forms. In same kind of carbon, you can develop by one method, which is conducting, semi-conducting, and insulating also. So carbon, many things is already written in literature. I'm not going to detail that one. So its melting point is more than 3000 degrees centigrade. Atomic radius, I already told you in my earlier slide. And it is basis of organic compound, all organic compound. And 10 millions, nearly 10 millions, you can say, carbon compound already discovered. So this chemistry is all known as organic chemistry. So chemistry people knows better than me. There are 2 kind of chemistry. One is inorganic chemistry, another one is, you can say, organic. Now, it is if you are dealing with properties, then it's a physical chemistry is also going to exist. So carbon is a wonderful material as far as material science is concerned. Next one, please. Yeah, so I already told you that carbon exists in different shape and size according to their bonding. In earlier slide, in semiconducting materials and some other kind of material, I already told you that on basis of bonding, on basis of nature, on basis of state, you can define a material in different way. So, on basis of bonding, there are 3, you can say, allotropes of carbon. It's already in nature. One is known as graphitic structure, which is known by bonding. It's known as sp2 hybridization. sp3 hybridization, that one is known as diamond. Next one, please. Yeah. So carbon exists into three forms. One, I already told you, on basis of structure, and that one is you can say known as a diamond. Another one is known as graphite structure, and next one is known as carbon nanotube or fullerene C60. So something I am dealing with carbon, so I am not going to touch about diamond, and you can say another one part. So diamond I am not going to touch, but of course I am going to touch something about graphite kind of material, particularly known as graphene or carbon nanotube. Next one. Yeah. So this material, particularly I am talking about carbon nanotube, which is very good material. Everybody knows that if you have carbon-based material, carbon may be rod type of shape, or maybe length or height. If it's you can say dimension one between 100 nanometer, then it's known as nanomaterial. So anybody, if you want to discuss with nanotechnology or nanomaterials, everybody, or anytime you can find something related with carbon nanotube. So this one is a very, you can say, fantastic material which is discovered by human being. Accidentally, I can say, because accidentally people have discovered too many things, which is not possible by physical. So most of material, you can say, discovered in nature by accident. So carbon nanotube, you can say, also a one very good material for that one. Next one. Yeah. So I think this slide is looking like a little bit about, you can say, something about science of materials. So I already told you that tube means tube. You already know. So you have a carbon-based allotropes, and one layer of carbon is simply known as, you can say, graphene. Graphene is discovered from, you can say, graphite sheet. Graphite is a layered kind of carbon-based material. So one sheet of carbon, which is very not easily, you can say, separate it out, is known as graphene. So when you are going to mold it, like a paper, I can mold. If suppose I have a one paper, I can mold in different way. I can say by taking one example, because I am in my home, so no problem. I think I am taking this simple paper. So in this simple paper, you can say in this paper, I can mold in three ways, either by length, either by height, or either by carbon. You can say corner, sorry, not carbon, corner. So if you are going to fold it according to their either length or breadth or height, or you can say in carbon, you can tell these materials as a different kind of things. And this property is known as chirality. So carbon atom arrange themselves in a hexagonal bonded pattern in form of tube, which creates many centimeter long bucky tubes or nanotubes. And I already told you that this property is known as chirality. So chirality is defined by a vector, which is known by chiral vector C, and C formula is Na1, Ma2, where A1 and A2 are unit cell base vector, and on basis of that one, on any one state, either by length or by corner or by breadth, you are going to mold it. You can find a different shape of carbon-based material. Next one, please. So chirality-based material, I already say that one layer of carbon-based material is known as graphene. So many possible way to form a cylinder. You can maybe put it by, you can say, length, maybe breadth, and maybe corner. Only three possibility. So if you are going to rolling it along one of the symmetrical axis, that one is given you either a two kind of, either a zigzag tube or an armchair tube. Right now it is already seen here, zigzag and armchair tubes. So it's depend on basis of which kind of dimension you are going to mold this carbon nanotube. And it's by chirality vector formula, each pattern have different property. So rolling it along one of the symmetrical axis gives you a symmetrical tube that is either a zigzag tube or maybe armchair tube. Rolling it along non-symmetrical axis, I am talking about, it's a, you can say length size or breadth size. You can maybe got another kind of carbon-based material. So chirality is a parameter which determined by how many times one has to move in either A1 direction or maybe A2 direction, or maybe you can say corner direction. Next one, please. Yeah. So I already told you that on basis of that one, people have synthesized carbon nanotube. Synthesis is another kind of things which I am going to tell you in my coming slides. So electrical conductivity, I am talking about this, why this carbon nanotube was very important. On basis of this chirality parameter, you can define a single one materials into two nature. Its chirality vector parameter CH means chirality, you can say vector is defined by Na1, Ma2, and it's already defined if 2n plus m by 3 is integer value, then your same carbon-based material, carbon sheet, or you can say graphene sheet is metallic. Otherwise, it's semiconductor. So this same carbon material either in metallic nature or semiconducting materials, or you can say semiconducting nature, on basis of which chirality vector or which length, breadth or corner you are going to fold it. Next one. Yeah. So carbon nanotube is a very important material, and why it's much more important, I am taking about some properties of carbon nanotube. You can see its current capacity, heat transmission, and temperature stability. I am taking 3 parameters. So carbon nanotube is gigaamperes per centimeter. And if you are simple telling about one good, you can say copper wire, it's already value is seen here. So its property is fantastic. What kind of material or what kind of carbon nanotube you are going to discuss, either zigzag or chiral or maybe armchair. Its property is totally different, and its each parameter is much more superior than any well-known, you can say, conducting material. Temperature stability, heat transmission. Next one. Yeah, so why nanotube? People always say that nanotube is very important. One, already play a very dominant role, one property or one phenomena, which is known as aspect ratio. Because aspect ratio is very high of this kind of. What is aspect ratio? It's a simple formula, length upon diameter. I already told you that if you are talking about one-dimensional material, two-dimensional or three-dimensional, one size may be in between 1 to 100 nanometer. So either or diameter. If any one parameter in between 1 to 100 nanometer, you can see your aspect ratio is always comes more than 1000. And if you have such a high aspect ratio, this one is the beneficial property of any nanomaterial or any nanotubes, you can say. So length, people have, you can say, carbon nanotube in different length, micrometer size or maybe millimeter size also. So if you see its length in millimeter and its diameter in 1 to 100 nanometer, then of course your aspect ratio more than 10,000. That's why these kind of tubes are conducting. It's play a very vital role in any kind of electrochemical device. Next one. Next, please. Yeah, so some other property I already mentioned, modulus. It's a very good in comparison to well-known, you can say, conducting material. Particularly for mechanical people, this slide is much more important. You already know that toughest material, I can say, high strength steel, every property is already known, maybe tensile strength and other things. And carbon nanotube is always much better than far away from these kind of conducting materials, or you can say stainless steel or other kind of aluminum or high strength steels. Next one. Yeah, so mechanical property, people have already discovered from other groups and many other literature that nowadays carbon nanotube, people already believe that it's a very rigid material. It do not make friendship with other material. But now you can develop a flexible nanotubes. And people have already discovered by animation, synthesize the material where these nanotube are flexible. So if you have a flexible kind of materials, you can very easily mold it in any kind of that. So why people are now mold it. Now people have embedded this flexible nanotube inside, you can say, polymer matrix or any other matrix, and then make a very good, you can say, flexible nanocomposite material. Next one. Yeah, so people already knows that there are two kinds of nanotubes, carbon nanotube. One is known as single wall carbon nanotube. Another one is multi-wall carbon nanotube. So one picture I have already shown you where too many layers embedded in between them, and that one is known multi-wall. The two inside that one. Now same kind of in single wall carbon nanotube or multi-wall carbon nanotube. Going to synthesize, you always find a two kind of structure. If you have carbon nanotube, then you are lucky guy because its property is much better. Nowadays, people believe that after research, the single wall carbon nanotube, many aspects, I'm talking about every aspect, many aspect is properties much better than multi-wall carbon nanotube. So you can synthesize carbon nanotube or multi-wall carbon nanotube according to procedure which you follow with. Next one. Yeah. So now I am coming to little bit about, you can say, synthesis of nanotube. Many literature already exist, but the most important things is that you are getting a good yield of carbon nanotube, a good quality of carbon, because you are dealing with nanomaterial. If you are dealing with nanomaterial, of course, it's very lightweight. People, according to going to develop any, you can say, everybody concerned about a microgram or gram. Carbon nanotube easy task. Carbon talking about pure carbon nanotube in a gram scale or bigger. People have discovered, everybody, you can say, people have anything, I think every mind is vibrating. So people have discovered a very, you can say, good method, and that one is known as Hammer's method, using which you can very easily develop a, you can say, reduced graphene oxide, and purifying or maybe some synthesis, you can really going to convert these kind of okay, synthesis already in literature, which going to tell you some, you can synthesize it. Single wall carbon and multi-wall carbon nanotube. So electric arc discharge, chemical which is known as CBD, laser ablation, flame synthesis, electrochemical method. These are common methods. Apart from now, we have discovered too many methods. But of course, you can believe about. So parentship deal by these kind of methods. People have refined methods and now discovered too many methods. So one by one, I think electric arc discharge, something I'm going to tell something about electric arc discharge method. Next one. Yeah, so these are the four, you can say, most important method using which anybody can develop a single wall carbon nanotube or multi-wall carbon nanotube. Next one. This is, I already told you that chemical vapor deposition is one of the method. So chemical vapor deposition known method, and then I am coming about arc discharge or laser. So chemical vapor diffusion, next one slide. Yeah. So CBD, you can say synthesis over CBD comes to arc discharge and laser ablation. Laser ablation means arc discharge means where you are going to take a two needles mechanical people knows better than when you are going to weld anything. So you are taking a very good conducting, you can say discharge, arc discharge method. You can take a needle, put in some electrochemical potential on that one, going to touch with conducting material, then there is arc discharge going to happen. So vapor is going to create. Same method you can make these carbon nanotubes. So that method is known as arc discharge method, where vapor is created by an arc discharge between two carbon electrodes. So you can take a two carbon electrode, conducting carbon electrode, put some potential, then whenever it's going to be coming in contact, this vapor is going to create without catalyst or with using catalyst. So that is known as. In laser ablation, I think one is going to use in place of these two carbon electrode. High power laser, where you can see one high power laser beam impinges on the carbon coating feedstock. So carbon coating, carbon containing feedstock, there is a kind of material, bulk material, where this laser is going to play a dominant role, and it's going to vaporize this carbon type of carbon containing feedstock, and you can get a very good nanotube. But problem with these materials are laser ablation, that you produce a very small amount of nanotube. If you need a very bulky amount of carbon nanotube, you never go with this laser ablation, because you get a very good, you can say pure carbon nanotube, but yield is very small. So of course, many methods are in literature, popular in literature, where people can produce more carbon nanotubes. Next one. Yeah, so in case of carbon nanotube, in general, carbon nanotube CBD methods results in multi-wall carbon nanotube or poor quality single-wall carbon nanotube. Single-wall carbon nanotube or multi-wall carbon nanotube, you cannot say one method. Whenever you are taking materials and going to put in, you can say same atom, then you can structure, it's either you can say single wall carbon nanotube or multi-wall carbon nanotube. So the single wall carbon nanotubes, which is produced with chemical vapor deposition, having diameter, of course it's large diameter, which can be poorly controlled. That's why using CBD, people have already put in research that time they are getting much more quality of multi-wall carbon, you can say, rather than single nanotube. But on the other hand, this method is very easy to scale up. It's easily get a commercial stage production. So if you are not bother about purity point of view, this one is very common method. You can say CBD method, where you can produce a net amount of carbon. So most of industry following this rule. Next. Synthesis of carbon nanotube, I already told you that putting a carbon gas phase. Gas phase means either you are talking about or CO or C2H2 gas, acetylene gas, and using energy source you can produce. Energy source you can maybe build, or you can maybe purchase from any other thing. So plasma state coil, you can put in to a gaseous phase to carbon molecule. So simply it's showing that you have a quad tube where you can say you can put your carbon source in just a quad tube. There is a medium carbon, and then you can put a this kind of plasma coil and generate a temperature nearly 720 oven. And if you are putting in gas phase of some other gas CH4, it's going to decompose. And going to decompose, then you got a good material on the surface of that one, is scraped it, and then you can purify it and put it in microscope. You can find either it's a carbon nanotube, single wall carbon nanotube, or multi wall carbon nanotube. So the energy source particularly by these kind of furnaces, is going to crack these carbon molecules, which is in form of gaseous, to reactive atomic carbon. Next one. Yeah. So in a continuation of that one, what I want to say that if you are going to put a too much, you can say temperature nearly more than 700, the carbon diffuse towards the substrate, which is heated and coated with a catalyst. You can use catalyst if you want a fast reaction. Otherwise, without catalyst, it's going to be crack these carbon molecules, but it is taking a longer time. So I think no one have patience. Everybody know that homeopathic medicine is much better than allopathy, but we do not have so much time, so we are dependent on catalyst. So CBD is a two-step process. If you want a fast reaction, if you do not have enough patience, then you have to produce a catalyst. Catalyst is doing nothing. Catalyst is just, you can say, moving this reaction very fast. The speed of this reaction is going to be fast if you are going to use a many catalysts already playing vital role in that one. And then actual synthesis of nanotubes. So there are in CBD two processes, one without catalyst or with catalyst. So catalyst is generally prepared by many methods, sputtering, a transition melted into substrate, and then either using chemical etching or thermal etching or thermal annealing to induce catalyst practice nucleation. Thermal annealing results in cluster formation on the substrate from which the nanotube will grow. So this one makes your reaction fast in comparison to earlier one without catalyst. Next one. Now CBD defined by many ways. You can say plasma enhanced, where you can just generate a plasma to crack this carbon thermal. Thermal means just by thermal heating more than 700 centigrade, which you can produce by any oven, you can crack these carbon molecules, gaseous molecule into, you can say, carbon reactive molecules. Maybe laser assisted CBD, where laser is going to put a strong laser on that one, and this plasma or thermal is just replaced by a laser light. Then alcohol catalytic means where a catalyst is made by alcohols, which may be moving this reaction very fast, and you can get a very good quantity of very good yield, or not, you can say quantity of carbon nanotube. Then vapor phase growth, aerosol supported carbon CBD method. These are several methods. You can say sub branches of CBD method, chemical vapor deposition. Next one.
Hope you are concluding, sir.
Yeah. Next one. I think now it's complete. Yeah. So plasma enhanced CBD. Now, Dilip, I have how much minutes? According to that.
You have already done, sir.
Yeah, okay, I already done.
Yes,
Then
sir.
I think I am going to move very fast. I think next one, please. Yeah, so plasma, thermal, and you can say thermal laser assisted. I already told you that put laser in place of that one. Next one, flame synthesis, where you can generate a flame and other things by using this and crack this carbon molecule. Next one. Yeah, so one small metal particle in single catalytic vapor deposition. Next one, please. So sonochemical method is another kind of method. Anybody can go through literature and find it many more things. Functionalization of carbon and then, yeah, I think now I am going to conclude that one, my own session. So using synthesis method, various synthesis method, you can say anyone can easily develop a single wall carbon nanotube or multi-wall carbon nanotube, and these are rigid materials. Now you can say very recently it is discovered that now it's a flexible nano, you can say composite material and nanotube materials. So if it's a flexible, you can mold it or maybe embedded into polymer matrix. It can be good, develop a very good conducting material, because the thing is that I have already shown in many slides, it's mechanical property, electrical property. maybe structural property is very good if you are going to compare with any conducting material. So people have already discovered advanced composite, advanced, you can say, polymer-based nanocomposite, polymer-based carbon reinforced material, particularly for aviation energy. And in my own laboratory, we are developing this carbon nanotube because I have not prepared for my own work, which is related to my particular work in supercapacitor area, where we have synthesized this, you can say, reduced graphene oxide using plastic waste. During COVID period, what happened? Many students are throwing this plastic bottle. So we have processed this plastic bottle into reduced graphene oxide, and we have used or prepare two kinds of electrode. Means one is, you can say, working electrode, another one called working electrode and counter electrode, and in between that one there is a sandwich polymer electrolyte. So same polymer electrolyte you can use sandwich between two carbon based electrode, you can develop a supercapacitor. And same, you can say, polymer electrolyte, if you are just embedded in between, embedded or maybe placed in between working electrode and counter electrode, you maybe develop a dye sensitized solar cell. So in my own laboratory, we are using this carbon nanotube to develop our carbon-based material, to develop, you can say, a very good polymer nanocomposite for electrolyte material, and particularly this bare carbon-based material for electrode material. And we have developed a very good, you can say, 1 by 1 centimeter dye sensitized solar cell along with 1 by 1 centimeter square, you can say, supercapacitor kind of electrochemical device. So thank you for your attention to learn, at least maybe listen this long lecture, you can say 1 hour, more than 1 hour. And so if you have any question, I'm very happy to maybe give answer.
Thank you very much. Thank you very much. It's a long lecture. That too, everything is considered nano particles, nano materials. Thank you, sir. Dear faculty, can anyone have doubts? You can clarify the doubts.
I think colleagues have no doubt. If you are any colleagues is going to give a good lecture, so I must thank, and I can say that my email ID always with Dr. Dilip. If anybody want to work with my own group or any kind of help, if I can help in my own laboratory or point of view, I am always ready to help all of you, particularly if you are working with polymer nanocomposite or you are going to develop a good supercapacitor or dye sensitized solar cell. So thank you for giving me this opportunity, and nice, you can say, introduce it faculty member which is situated in South Sur. So Dilip, I must say,
sir, supposing if you a multi-wall carbon tube is produced, do they have any restriction on the diameter and the interrelationship between the two concentric tubes?
Yes. If you are going to synthesize a carbon nanotube, you can say, you never knows that whatever yield material you are getting, it is either multi-wall carbon nanotube or you can say single wall carbon nanotube. So single wall carbon nanotube, you can consider it as a tube structure of graphene, single layer of carbon. That's why its conductivity and other properties are very much far away from multi-wall carbon nanotube. Multi-wall carbon nanotube, you can maybe synthesize, you can consider it as too many carbon, single wall carbon nanotube embedded in a helical structure. And embedded means it's not flexible as much as I told. It's a rigid material. So they intercollecting layer between one carbon nanotube, you can say single wall carbon nanotube, another one single wall carbon nanotube or multi-wall carbon nanotube. It's not easy. It's not flat. That's why too many distribution or too many distractions came when two layers of single wall carbon nanotube going to joint and make a multi-wall carbon nanotube. So of course, single wall carbon nanotube people always prefer, but it's very hard to get it.
Okay, sir. Okay. Thank you, sir. Thank you very much, sir. This is very relevant to the material science and mechanical people. So we are also from mechanical. We learned many things, sir. Thank you for enlightening us, empowering us, educating us these nanomaterials in its chirality and zigzag angle. Everything is nice, sir.
Thank you.
Thank
Thank you,
you, sir.
dear
Thank
sir.
you very much.
Should I leave
We would
now?
like to associate with you in
Yeah.
future.
Yeah, thank you. Thank you, Dilip.
Thank you.
Now I think my home ministry is calling me, so please permit me.
Yes, sir. Sir, you are most welcome, sir.
Yeah.
So we'll start. I mean, it's our time to start second session, sir, of the day.
Thank you. Thank you.
Thank you, sir. Thank you very much. So, dear faculty friends, we have come to the end of the first session of the day. I hope you are all enjoyed this nano, but indeed, nano carbon tubes are very efficient allying elements. They are not bulk material, but they're allying elements. Next session we have today on energy storage technologies for renewable energy applications by our colleague, faculty of the University JNTUK Technological University, Dr. G Anil Kumar. He'll be taking a session on renewable energy applications. I would be very happy to introduce to the faculty, research scholars, our guest speaker of the second session, Dr. G Anil Kumar, Assistant Professor of Institute of Science and Technology, School of Renewable Energy Engineering, JNTUK Kakinada. He has completed his MSc Electronics, MTech in Energy Management, PhD in Energy Engineering. He had also other qualifications, diploma in embedded systems. He had successfully published 20 research publications and 2 international conferences. He had 20 years of teaching experience, and he is with us to deliver today's talk, and he has successfully guided 30 PG projects. With the short introduction, because we are running out of time, I would now call upon Dr. G Anil Kumar to take up the session. Welcome, sir. Anil Kumar, G Anil Kumar. He has joined. Am I audible? Dear participants, am I audible?
Yeah, you are audible, Dilip.
Yes,
but
sir. Yes, sir. You're audible, sir.
you are audible.
So are you able to hear me? This is Anil Kumar.
Yes, Anil, Dr. Anil, you are audible. You are also audible.
Okay, what about my screen presence? Is it
No. I will stop sharing my screen. Then you can share the screen.
Okay.
At least you can turn on your video.
Okay.
Very good, Dr. Anil. So I'm stop sharing my screen. You can share your screen. Thank you, Dr. Anil.
Yes, sir.
Yes, please.
Is it shared, sir?
Yeah, your screen is visible and your voice also clear.
Okay, sir. The screen is visible for you.
Your screen is visible to us,
Okay.
all the participants.
Yes, sir. Screen is visible, sir.
Yeah.
Okay, good evening to all of you.
Very
Here,
good evening, Anil.
good evening to all of you. I'm really happy to give presentation on energy storage technologies for renewable energy applications. Here, regarding this, that means storage is a major issue with the increase of renewables integration, but decentralized energy sources that penetrate power networks. Not only it is a technical solution for network management nowadays, ensuring real-time load leveling, but it is also a mean of better utilizing renewable resources. Okay, but by avoiding load shedding in times of overproduction, and sometimes coupled with local renewable energy generation, decentralized storage would also improve power network sturdiness through a network of energy farms. That means either it may be a solar array farm or a wind farm, like that, all renewable energy sources, so that it can supply a specified demand zone. Okay. Now, hoping for this one, that means this is the main outline. That means this is the main cause, this is the main objective of selecting this topic, energy storage technologies for renewable energy applications. However, for renewable energy applications, the term here I had selected for renewable energy applications means here for all the applications that regular energy was going to, conventional energy was going to satisfy. But whereas, especially as long as the renewable energy was going on, that means the intermittency is the main problem regarding renewable energy nowadays. Okay, that is not nowadays. That means renewable energy is the most important problem that we are going to encounter with renewable energy is intermittency. In order to avoid this intermittency, the only solution that we are having as of now is to make use of energy storage technologies. A wide variety of renewable energy sources are available. Okay, and a wide variety of methods are available in order to tap the power. And at the same time, a wide variety of energy storage technologies are also available. And it is a complete diverse field, both from energy storage technologies point of view, as well as renewable energy applications point of view. That means from a miniaturized product to a macroscopic product, we are having a diverse nature of both sources as well as applications. In order to bring out an integration between these two applications, sources to the applications, real-time applications. Okay, here I would like to present about what is the current scenario, what is the major problem, and I start with after discussing that major problem, okay, that has prevailed nowadays. I will move on to what kind of energy storage technologies are available. I'm not going with what kind of renewable energy sources are there, because it is well known for all the people here, for both faculty from mechanical engineering as well as from electrical engineering. I hope so. And therefore, here, what kind of energy storage technologies are available as of now, and then we are going to compare them. Okay, along with this one, during this discussion of each and every technology, I will discuss about the applications of each and every storage technology. I tried to cover in this presentation, I will try to cover the maximum energy storage technologies as I can do. Okay, but okay, I will try to cover them. A huge amount of energy storage technologies are available from wide varieties. Okay, we'll start with the basic definition for energy. We know that energy, because as it is a diverse topic, okay, that means broad topic. Okay, I will start with energy itself. We can be defined as capacity to do work. Okay, that work can be done in many ways for various applications. Okay, now how we are going to tap that energy, how we are going to utilize that energy for, and why we are supposed to store energy. What is the need for energy storage? Okay, Because what is the need for energy storage means, from the grid point of view, the problems are different. From the local domestic point of view, the problems are different. And from commercial point of view, the problems are different. That means here we are having a wide variety of, that means demand versus supply. There is a gap between demand versus supply, because as the population was increasing and the quality of life was increasing, the demand for power also increasing, because everyone was going to make use of the demand for energy is more. As the GDP of a country increases means the energy consumption is also more. Whenever the energy consumption increases, the country was, one can say that the country was developing like that. That means for the development of a country, we are in need of energy supply. Okay, as therefore, as the population increases, energy demand also increases. As the energy demand increases, the supply should also meet the demand. But in order to, but there is a gap between these two. That's why government has taken so many measures. Government was taking so many measures in order to build, in order to overcome this gap. Okay, here in my first slide, here I am going to show in the second slide. Here I had shown a picture which was going to exhibit the complete whole energy system, which was going to show you the complete energy system, whole energy system. Here you can see that the existing most of the coverage that has been done, most of the policies or most of the technologies that has been available, are the assessments or optimization models that are available are shown here with the three kinds of this one. That means bold letters, grid scale, you can see in the picture, wider electricity system, okay, and whole energy system. Okay, therefore here one can say that, that means here as at international level we are being request, that means we have to go for we have to meet the low carbon energy system. We have to come up with a low carbon energy system. Therefore, from our national wise, if we want to modify or if we want to develop our energy system or grid storage system into a low carbon energy system, okay, one has to consider the new storage technologies that are designed to contribute towards this low carbon electricity system. Therefore, one has to consider all these individual energy systems. That means here one was going to focus that you can examine from this figure. Within the grid scale, there is an energy storage. Within the wider electricity system, there is an energy storage. And when coming to the wider energy system, there also you can see the storage in different levels, at different levels. Therefore, one has to integrate all different kinds. That means not only electricity, because it is the only most convenient form of energy. Okay, that's why people prefer electricity only. And coming to the thermal energy and other kinds of gaseous energy, okay, liquid energy, liquid-based energy, solid-based energy, energy available in the solid form, liquid form, as well as gaseous form. Okay, not only electricity, but also these three forms should also be taken into account to come up with a common unit of energy transition, so that one can accomplish or one can sort out or one can bring out a low carbon energy system. A new challenge for electricity systems is the increasing penetration of these renewable energy systems. Okay, these low carbon solar, wind and wave technologies have high capital costs and negligible operating costs, but the intermittent outputs cannot be easily forecast or controlled. Therefore, small penetrations of intermittent generation can be incorporated through standard flexibility electricity generation. However, as renewables account for an increasingly large part of this generation portfolio, generally two kinds of concerns will arise. Okay, first one, at times of high demand and low renewable generation, deficits occur that can affect the stability of the entire electricity system. Okay, and at times of low demand and high renewable generation, surplus electricity is generated that must be stored alone, or if you are unable to store, we have to lose it. Okay, these electricity systems, that means one is high demand and low renewable generation. Second one is low demand and high renewable generation. It creates an imbalance. It creates an imbalance. Therefore, there is a dire need for developing an energy storage device. Okay, and that too, one can see that energy, because a layman knows energy storage as a battery only in his own house, but they doesn't know about a grid level. Okay, for coming to the educated literate people, they know about the grid as a energy storage to the maximum extent. What about the integration with all these individual energy storage devices? How come? Okay, how we can integrate individual at various levels, at short-term levels, at mid levels, and at long-term, long duration energy storage levels. How can we integrate? Thus, if we are able to do so, then we can come up with a low carbon energy system. That is the concept of this whole energy system. Now coming to the next slide, slide number 3, there you can see that, okay, energy storage applications into grid. Okay, it was going to give a real-time picture of the entire grid position from grid energy storage, where you can see the left side, you can see the legend regarding the symbols for load, storage, and power plant. Okay. On the right side, you can see the nomenclature for A, B, C, D, E, F, G there. You can see that about renewable energy generators, commodity arbitrage, transmission support, and distribution difference, power quality issues, and DG support off grid. Okay, it was going to give the complete picture of what the energy storage is, what is the necessity of energy storage is in real-time grid. And then in the next slide, you can see that energy storage systems. Okay, and one can see that means here earlier what we can say that people was going to think of, okay, people was going to think of generally the ESS can be used to reduce the peak of or the traditional electricity value chain. It was earlier, but here I had shown the existing sixth link also. Earlier, people was not going to consider energy storage system. Even the governments now also are going to, even for example, our government has given a clear roadmap up to 2032, okay, about how to integrate these renewables to medium bus bars. Okay, thus that means not only medium bus bars, but also low voltage bus bars also. Okay, thus it is that means every country was focusing on these energy storage systems. They have included or incorporated this energy storage system also in their electricity value chain. Okay, now this figure was going to represent the electricity value chain. Okay, where we can observe the sixth link by integrating the existing segments of different fuel, energy sources, generation, transmission, distribution, and customer energy sources. Okay, fine. Next, the slide was going to show about the classification of energy storage system. Now, slowly I completed my introduction, and slowly I am entering into the energy storage classification of energy storage technologies. Okay. Now here you can see that, as I already told you, there are a wide variety of energy storage technologies. They can be diverse field from mechanical, electrochemical, chemical, electrical, thermal. Okay. Now again, they have been subdivided into pumped hydro storage, compressed air energy storage, flywheel energy storage, and then here nickel based, okay, and lithium ion, metal air, so electrochemical batteries, flow batteries. Now I am going to discuss about those things in a detailed manner, that means from the fundamental point of view, like that. Okay, that means I am going to here discuss about the each and every the physical principle involved in those energy storage technologies, and finally I am planning to conclude with the comparison and when to select a particular energy storage for a particular application, like that. Okay, now we will start with in the next slide. You can see that slide number 6. You can see that, okay, we know that energy is available in different forms. Okay, energy can neither be created nor destroyed, we all know. Okay, but it transfers from one form to another form. This point is very, very important, okay, in energy storage. Okay, because the most convenient form of energy is electricity for all of us. Okay, for a customer also, customer always prefers electricity, energy available in the electricity form as the most preferable one. The entire gadgets or the entire appliances are based on that AC energy earlier. Now slowly they are moving towards DC, and even in the coming era, we are going to come up with a DC grid, something like DC grid like that. Now here in this slide, I had been presented with a table has been shown that fundamental forms of energy and energy storage that is available in that particular form of energy. That means that particular form of energy is available as a storage in those areas. That means, for example, chemical energy can be absorbed in fossil fuels in the form of coal, oil, hydrogen gas storage, and thermal energy, heat energy can be utilized in hot water storage or ice storage. Okay, and coming to potential energy, pumped hydroelectric, which we already know, compressed air storage, they are very renowned energy storage, which was going to serve the that means which was a long, and that means high-end energy storages. They are high-end energy storages, and that too, the cost per unit energy stored is also very, very low from both from economical point of view and technical point of view. They are very useful ones. Okay, and coming to kinetic energy, flywheels, they are used from small end gadgets to high-end, like artificial sun fabrication. That means a group of countries are fabricating that artificial sun, in which this flywheel is the energy. Flywheel is selected as the energy storage component in that one, and we will discuss that one in the coming slides. And electrical energy, we all know in the yesterday, as always are mentioned, supercapacitors and superconducting magnets and lead acid battery fuel cells. Not only those things, we will see some other electrochemical batteries also. Now, what is important here is that the important parameter, because as just now I told you, there are wide variety of energy devices that are available, and each and every energy source or each and every energy form was going to have their own units, parameters, and all these parameters had been converted into a common parameter. Okay, here in this case, in this table, we can see that as megajoules per kg, expressed in megajoules per kg. The individual calorific values, those things everything has been converted into here megajoules and placed here for the sake of comparison, where we can see that hydrogen gas storage was going to dominate. That means it was going to offer us about nearly 140, okay, and 140 megajoules per kg, okay. And second thing is that even for fuel cells also was going to offer a very good energy density, okay. However, it depends upon the mass of the gas storage tank that we have been selected. Coming to the round trip efficiency, here, this one was going to show that this round trip efficiency means it is nothing but the amount of energy released when compared with the amount of energy that was output by input energy. But it is expressed the time. In other words, we can also say that the time it takes to switch on the power output also. Coming to this parameter, the electrical energy supercapacitors was going to dominate with approximately 95% of round trip efficiency, and whereas the least one is hot water storage, that is 50%. Okay, now we will move on to the next slide. That is very famous. That is here in this case, also see that about this classification. Okay, the cost of the peak load power generation is higher. Okay, in general. Okay, okay, this mechanical energy storage. Okay, and this can be stored either as potential energy or kinetic energy. A simple example of stored potential energy is the pumped hydroelectric energy storage. Okay, the weight provides the energy to drive the turbine. Okay, on a much larger scale, potential energy is stored as water in a pumped hydroelectric plant, or as a second one, compressed gas in an underground salt mine also. For the case of kinetic energy, this can be stored as the rotational energy of a flywheel. In case of mechanical energy, flywheel also comes under this pumped hydroelectric energy storage. Now, let me discuss about this pumped hydroelectric energy storage. And we know that the gravitational potential energy of water is used to drive a turbine. The dam of a reservoir, in this figure you can see absorb. The dam of a reservoir serves to contain a large volume of water, and hence a hydroelectric plant has inbuilt energy storage. In a pumped hydroelectric storage plant, there are two reservoirs, one at a higher elevation than the other. Okay, at times of low electricity demand, for example, during the night or during the weekend, okay, excess electricity is used to pump water into upper reservoir. Then when there is a high demand, water is released back into the lower reservoir through a turbine, thereby generating electricity. In practice, a reversible pump turbine unit performs both functions, okay, both under pumping mode as well as turbine mode. And here you can see that one more important, the amount of, now from analysis point of view, the amount of stored energy is generally given by E equal to mgh equation, where m is the mass of raised water, h is the height or distance for which the center of gravity of the raised mass of water is moved vertically, and g is the acceleration due to gravity. And the energy density of pumped storage system is rather low generally. Okay, for example, the energy density is 0.98 kilojoules per kg for a high difference between them, two reservoirs of 100 meters. But this low value of energy density is balanced or offset by the large amount of water that can be moved between the two reservoirs. However, pumped hydroelectric storage has the largest energy capacity of all storage systems, and that is the most economic one, followed by entire world. Okay, everyone prefers this one. Okay, and is also the most cost effective. Further, it is the most widely used method of large-scale energy storage, and in particular, it is used to supply additional energy to a national grid. Okay, even the most fantastic nature of this one is seasonal energy storage can be achieved by using this pumped hydro. Okay, that entire grid can be maintained based on this one. It also has the advantage that it can be switched on relatively quickly and can respond to rapid changes in power demand within seconds, taking into account those evaporation losses from the exposed water surface outside top of the water surface and conversion losses. Approximately 70 to 85% of the electrical energy used to pump the water into the upper reservoir can be regained, we can collect them back. Okay. Clearly, one can say that mass m and height difference should be as large as possible because E is directly proportional to mgh. If m and h are there, it is directly proportional to m and h because g is constant. Okay, therefore we have to focus on these two parameters. If I want to get more amount of energy, I have to focus on, the mass parameter has to be increased as well as the height has to be increased. Okay, so that the energy can also be increased. By having a large body of water located on a hill, but as high as possible above a second body of the water which is at ground level. In some places this occurs naturally, because naturally occurring there are certain locations that are available. Mostly these plants, pumped hydro plants, will be constructed in those areas only. Okay, while in others one or both bodies of water, sometimes we have to go for man-made kind of things, because some governments are trying like that, and some of them has achieved that one also. Okay, now coming to this pumped hydro storage, we can say that, well, now let us discuss about their advantages. They are really economic, as I already said, and they are very reliable, and storage capacity is very high, long life cycle, and high efficiency around 87%. We can say that. But always we are going to, where strength is there, weakness also comes into picture. The electric power, and here the disadvantages of this one, the electric power and energy density is very low. Most energy storage devices are going to be classified, that means they are categorized, performance will be studied based on energy density and power density. These two are very, very important factors. Okay, while assessing the performance of any energy storage device. It is a costly power generation because in order to construct a huge dam kind of thing, okay, generally the cost of that one will be more. But on the long run, okay, the power generated per investment cost is very, very low, because the cycle life is very, very long cycle life. Okay, now coming to the industrial applications, it can be used as that means especially the generating stations, transmitting stations, they are going to rely on this one as a backup power, as we already discussed. Now comes a very, very important discussion from my end, which you are unable to. This is an important takeaway from my end. Okay, which regarding pumped hydro storage. What are the novel hydroelectric storage ideas, concepts based on this power already existing, well-proven, successful pumped hydro storage system is that people are investigating on piston in cylinder kind of storage, energy membrane kind of storage, and the same concept. Okay, novel land-based and seabed pumped hydro configurations, offshore, that means within the sea, offshore lagoon and energy island storage. Okay, in this case, the piston in cylinder and energy membrane use pumped hydro techniques as usual to elevate a solid working mass, similar in principle to hydraulic accumulators. Where the remaining two, novel land-based and seabed pumped hydro configurations and offshore lagoon and energy island storage, they are going to rely on seawater or any free-flowing water. As the working mass in configurations, they differ in some respects from conventional pumped hydro energy storage. Further, in addition to these four, okay, people are focusing their research is on variable speed pumped hydro storage systems and using seawater for pumped hydro energy storage systems, underground pumped hydro energy, that means the reservoir was going to be, all these concepts, okay, was going to be placed artificially within the land. Okay, compressed air pumped hydro energy storage. Okay, that means the water will be pumped upwards. Okay, just similar to our regular pumped hydro, but it was going to this water which was going to pump upwards was going to, the air is already filled in a compressive tank, steel vessel. Okay, on upper reservoir area, and that air will get compressed when the water moves upwards. Then it itself was going to create an energy source. Okay, conversion and undersea pumped hydro energy storage also. These are the novel concepts, novel hydroelectric storage concepts that people are studying, and especially in countries like Finland area and Netherlands area, they are focusing on this kind of pumped hydro energy storage technologies. And now I would like to move on to now two more important thing is that, okay, recently a gravitational energy storage concept has also been arrived. That means a concrete blocks will be moved from lower reservoir, that is lower end to higher end. Okay, a large mass is raised or lower hydraulically during electricity surpluses. That means whenever we are having excess electricity is available on the grid, okay, one can make use of that one in moving these concrete blocks, okay, or a mass, concrete, usually a concrete disc. It is raised or lower hydraulically using that economical power. The aim is to create a smaller, cheaper system than pumped hydro, which is not limited to a small number of available sites. And these, that means whenever we are in need of power, again, that concrete block is lowered, and thereby you are going to run a turbine so that one can generate the power. Second one is one more important point, which has already been successful in European countries, that is advanced rail energy storage. That means at times of high demand, okay, whenever there is a demand, the train is written. That means whenever there is a surplus of energy, then the heavy electric train is moved to a higher elevation. Okay, and when there is a demand for energy, the train comes back. It will be lowered. Okay, the train is allowed to move downwards. The advantage of this technology is that there are no energy losses at all over time. Once the train has reached a high elevation, and it is particularly suited for dry regions where little water is available and high evaporation would cause hydroelectric reservoir losses. These are the emerging technologies which I discussed with you just now. Okay, we got based on pumped hydro storage systems. Okay, that means these technologies, in future, these technologies will play a key role in the energy storage. Now let's move on to the next kind of mechanical energy storage, that is compressed air energy storage. A compressed gas, here in this case, a compressed gas exerts a force on its surroundings and so has the potential to do work. We can compare a compressed gas to a compressed spring and Boyle, famous of his gas law, which was going to express springiness of air. Just as a compressed spring stores energy in the form of potential energy, so a compressed gas is also a store of energy, which we already know. We know the expansion and compression of ideal gases, and that these processes may be isothermal or adiabatic. Here, the considered example of an ideal gas contained in a cylinder with a frictionless piston, we already know this example, and processes that are quasi-static, that is where the piston is moved slowly so that the gas is never far from an equilibrium state. In an isothermal compression and expansion of a gas, the gas and its surroundings remain at constant temperature. In the compression stage, the work done on the gas is converted into heat that is passed to the surroundings. Finally, the work which it has to do to compress the gas from volume level 1 to volume level 2 can be obtained by integrating that pressure within these limits. That using the fundamental law which we from the Boyle's law, that is PV equal to nRKT with T constant, we can obtain that W equal to nRT log V2 by V1 ratio of those two volumes. Okay, where N is the number of moles of gas and R is the gas constant. We know that. Thus means when we expand the gas to its original volume, initial volume, again at constant temperature, the gas does an amount of work that is exactly the same as the amount we use to compress the gas. We all know all these things. This work comes from heat given up by the surroundings. We thus have a means of storing energy. This is the point which I want to highlight, for which I discussed all these things. Okay, that means it was going to exhibit that is one can store energy by using this concept. Because I know that the internal energy of an ideal gas, which is the kinetic energy of its molecules, remains the same as it depends only on the temperature of the gas, which is constant. This ideal isothermal and reversible process is 100% efficient, but in reality, it's not the case. We get as much energy out as we put in. An ideal adiabatic compression expansion cycle is 100% efficient, which we already know. Based on this compressed air energy storage concept has been built on. As we recall, in an adiabatic process, the system is thermally insulated so that no heat is lost to the surroundings. And in the compression stage, the work we do on the gas goes into raising the temperature of the gas, that is, into increasing its internal energy. When we then expand the gas to its original volume, the gas returns to its original temperature as it gives up energy to do the work to expand the gas. Compression and expansion. Of course, but as I already told you, in real time or in real life, okay, compression expansion cycles are not ideal. Isothermal or adiabatic processes, and their efficiencies will be less than 100% because nothing is perfect in this universe. However, by considering ideal situations, we can determine the maximum amount of energy that a compressed gas can store. The basic idea of compressed this air energy storage is, one can say that as a straightforward process. When demand for electricity is low, air is compressed and stored at high pressure. Then when demand is high, the compressed air is used to drive the turbine that in turn drives a generator that delivers electricity back to the grid. Large-scale storage of energy for a national grid requires very large gas containers and very high compression ratios. Therefore, geographically, we have to select areas where we can establish this kind of technology. In practice, compressed air plants have used salt mines to store compressed air at a pressure of approximately 70 bar. Okay, the main features of a compressed, one can see in that figure, you can see electricity in motor, compressor, valves, fuel gas initial ignition, combustion chamber, turbine generator, all, and compressed air, the cavern, you can see all these are the main important components. Okay. Air is compressed here and stored in an underground cavern or mine with a large volume of approximately 3 into 10 to the power of 5 meter cube. This is a volume, use volume. This compression happens rapidly so that the process is not isothermal and consequently the gas gets heated up. The plant machinery cannot function at high temperatures and the heat produced in the compression step must be, one has to remove that one. That means correct that one, gain that one back. Okay, and you can see that during, okay, we can see this is done by heat exchanges. One can make use of heat exchanges that transport the heat away or by dissipation of the heat in the surrounding rock. This cooling process maintained, that means by using the heat exchanger, we are going to execute the cooling process, which can be maintained by the stored gas close to the ambient temperature. This represents a substantial loss of energy and reduces the round trip efficiency of the system already defined, okay, output by input. When the compressed air is released to the turbines, the gas cools down because the expansion is rapid. The degree of cooling is also more, okay, and would stop the turbines to function. To prevent this, the compressed air is first heated up. This is done using a combustion chamber, as you can see in the figure at the middle, okay, where a fuel, typically natural gas, burns in the compressed air. The need to provide external energy to heat the gas further reduces the overall efficiency because we are using, in addition to this electricity, we are using the gas. Okay, that means a burner kind of additional energy is required. However, the amount of natural gas the system burns is roughly 1/3 the amount used by conventional combustion turbines, thus producing only about 1/3 of the pollutants. That is less pollutant. Okay, a typical value of round trip efficiency is approximately 50% here, can be achieved using this compressed air energy storage. And most of the energy storage, that means throughout the world, they are second after pumped hydro. People are the second choice for a long-term energy storage is, and even another word is seasonal storage also is compressed air energy storage. Although this figure may seem to be low, that means the round trip efficiency may be low. Compressed air is the only system that has a storage capacity which is comparable to pumped hydro energy. A new type of compressed air system, air storage system developed with the increased efficiency. In this new type, that means adiabatic based ones, the heat that is produced in the compression stage is used to heat oil or molten salt that is stored in thermally insulated containers. Okay, that means one can use a container. Like this stored thermal energy is then used to heat the compressed air before it is passed to the turbines. This system is called, generally people was going to call it as advanced adiabatic compressed air energy storage. And its principle of operation can be seen in this figure, slide number 9. You can look into that slide number 9. Okay, where you are going to have one additional component at the middle, stored hot oil tank or filled with molten salt, either with hot oil or salt, as it minimizes the loss of heat during the compression stage because of using that, removes the need for fuel gas. Now, whatever, because the reason for which we have noted that the overall efficiency was going down, now we are replacing that. Instead of fuel gas, one can use this molten salt stored hot oil. Okay, during the expansion stage, it is anticipated that, or it can say that here by using this change, okay, one can say that the overall efficiency of this kind of storage can provide us around 70%. It has additional advantage that the most important feature is that it was not going to release carbon dioxide gas. CO2 gas cannot be released. Okay. Now coming to the advantages and disadvantages. Okay. And along with the applications, it has been blessed with high energy storage capacity and low cost and long life cycle, and regenerations are also possible. System overall efficiency with everything taken care of can approach up to 80%. Okay. And coming to the disadvantages, some environmental issues and local limitations or location limitations are there. Okay, because exactly identifying the area where we can, without any loss, we can compress the air. Variable system efficiency, because generally a rocks kind of system or cavern has to be identified, because its efficiency is variable, not constant throughout. That is one more important problem. Coming to applications, renewable energy applications, it can be used for load balancing. Okay, generally this is a major problem with encountered by the grid management. Okay, for load balancing or energy management issues. Okay, for load balancing and during power outages, one can make use of this one, just like pumped hydro. This can also serve the purpose for energy management of grid. Now coming to the most important one, as again I am the emerging technologies in area based on compressed air energy storage. Emerging technologies in this area are diabatic compressed air energy storage and hydropneumatic storage, and a hybrid combination of compressed air energy storage with concentrated solar power and adsorption based enhanced using the concept of adsorption. Okay, that means here where you are going to that means the molecules are attached to the surface. Okay, compressed air energy storage and isothermal compressed air energy storage. These are the emerging technologies based on this concept. Okay, that means the feasibility of this one, people are studying about the feasibility of this one, especially European countries are very serious about these technologies regarding the out of which some of them like diabetic has seems to be promising, and we have to wait for the reports regarding the remaining ones. Next comes here liquid air energy storage system. Okay, and liquid air energy, this is also comes under mechanical energy storage system. Okay, here a liquid air energy storage is this system comprises of a charging system, an energy store, and a discharging system. Because the basic definition of an energy store is the purpose is to charge, store, and then discharge. These are the three basic steps that has to be followed by any energy storage system. Energy storage, it has to incorporate these three steps. Okay, therefore while designing, and that means if you go for any electronic devices during ramp up or ramp down of energy signals, that means voltage or power signals, they are going to focus on those things also. That means they are going to match up with that ramp rate. Okay, like that here also from mechanical side. Okay, the charging system is an industrial air liquefaction plant where electrical energy is used to reject heat from ambient drawn from the environment, generating liquid air. That means low temperature air or low temperature nitrogen. Generally, it will be called as cryogen. The liquid air is stored in an insulated tank at low pressure, which functions as the energy store. When power is required, liquid air is drawn from the tank, pumped to high pressure, and evaporated. This produces gaseous air that can be used to drive a piston engine or a turbine to do useful work that can be used to generate electricity by running the motor. There are various categories here in this case of this LAES, okay, or we can say that various categories means here we can say that there are design variants that are available. One can use a gas turbine, one model, a air expander model, and storage medium. These are the three different design variants. That is, liquid air is evaporated in the first. That is, if you are using gas turbine, liquid air is evaporated, then combusted with the fuel, usually natural gas, and expanded through a gas turbine to generate electricity. And air expander and liquid air is evaporated and expanded using heat generated during air compression or from an adjacent industrial process in an air expander, anywhere. And usually the storage medium can be air, nitrogen, or other air or compressors, liquefaction unit, low pressure, insulated liquefied air tank, and evaporation unit, air expander, gas turbine, and electric generator, cold storage, heat storage, they are optional. Okay. Gas turbine, cold storage, and heat storage are optional. Okay. Using this, the power range that we can get is around 5 to 650 megawatts. Energy range is around 10 megawatt hours to 7.8 gigawatt hours. Discharge time is around 2 to 24 hours. Cycle life is around 22,000 to 30,000 cycles. Life duration is around 30 to 40 years. Here reaction time is greater than or equivalent to around 5 minutes, and efficiency of this one is around efficiency is around 50 to 100%. The power density or energy density, we can say it as energy density is around up to 230 kilowatt hour per meter cube. One can expect. Okay, and this is about the liquid air energy storage system. Okay, and coming to the flywheel energy storage system, one can say that means one can focus on. If coming to liquid air energy storage system, the advantages are they are going to offer excellent power density as we have discussed just now, and energy compared to battery, its counterpart battery energy storage system. They are going to exhibit faster and shorter response, high efficient, and independent supercapacitor is a major the major disadvantages here. Okay, coming to industrial applications, it can be used to control voltage as well as frequency. Okay. Now let us move on to the flywheel energy storage system. Okay, you can see here flywheel, as I already told you in the beginning, forms of energy storage. Flywheel energy storage is available right from our laptops to, okay, even as I already told you, artificial solar, artificial sun. Okay, a group of countries, US, China, even India is also participating in that one, in that program. Okay, and the Jet Propulsion Laboratories has developed this flywheel energy storage is for that one. That is continuous of energy generated from that artificial sun, for which they have selected this flywheel energy storage. And nowadays, just like electric vehicles, one more concept is that in automotive applications also, okay, a concept has been arriving. That means, I think so, it has also been proven also. And that means they are going to use flywheel as a regenerative system. Okay, that means which was going to offer, that means low energy consumption. That means the mileage issues, energy consumption will be low, and it is a very, and from emission point of view also, it is a green source of energy. Okay, therefore these also, there are wide variety of applications, okay, from low energy range to high energy range. Okay, here you can see in the figure, you can see it is mounted on the same shaft as a combination of electric motor as well as generator. That's entire energy storage system. Okay, the electric motor accelerates the flywheel here to high angular velocity. The generator produces the electrical power on demand by deceleration. Okay, initially from motor it was going to gain the acceleration. Now when required, it is allowed to in decelerating mode. Energy losses due to frictional forces are minimized here in this case by mounting the flywheel assembly on a magnetic bearing. Okay, in an evacuated. Entire setup has been placed in an vacuum chamber. Okay. Now you can see that figure in this slide. Okay, and now the flywheel is mounted. We have seen prevents any corner. The round trip efficiency of this one is around 90%. And they can energy storage is from, they can spin from 25,000 to 50,000 RPM, and carbon fiber flywheels can be used to achieve energy storage densities of around approximately 0.25 megajoules per kg, while typical storage capacities will range from approximately 10 megajoules to 2 gigajoules. Flywheel storage system need little or no maintenance and have long lifetimes. They last for several decades or more. They can also undergo a very large number of charge-discharge cycles, around 1 megacycle. Okay, approximately 10 power 6. Their disadvantage is their relatively high capital cost. That is a major disadvantage, and requires strong containment vessels as a safety precaution. Okay, and this increases the mass of the overall system. And we already discussed that toroidal one can use one flywheel supplies the field, as I told you just now, tokamak operation. Okay. And coming to the advantages, required low maintenance and long life cycle, and eco-friendly, as I told you just now, and excellent power response, high efficiency up to 90%, and high capability of energy storage. And coming to the disadvantages, it's high mechanical stress and more cost. Coming to industrial applications, they can be used for renewable applications and flexible AC transmission system, FACT devices, and for transportation also. And one more from the mechanical energy storage system, one more thing which is not shown here in the classification, but people was going to, as the literature was going to say that mechanical springs cannot, spring stores mechanical energy in terms of, in the way of potential energy form. When surplus power is available, to move the springs in a clockwise direction to store the energy. But during the peak demand for power, electricity is generated from spring using a dynamo. We can make a from low-level energy storages to energy level storages. We are discussing about them. That means in real-time applications, that means it's upon application. But not only that means application demand for that one we can this energy storage device appropriate, so that they will be appropriate particular application. Now we can move on to more in the next class. You can see that in the slide there is a comparison of low flywheel energy storage system, and based on this selection like material, electric machine, flywheel interface, electrical machine, environment, enclosure weight, main applications. You can see that in flywheel system it is, whereas in case of high speed it is a composite material, and we can use PM and permanent magnet storage, machines, okay, and a partial and coming to environment, vacuum, is partial vacuum in case that means the entire enclosure has to be evacuated. Okay, otherwise means influence of external surroundings may happen, and it was going to alter the operation. Okay. And coming to power quality, main applications, low speed flywheels can be used for power quality, whereas high speed ones can be used for aerospace. And cost of this, coming to cost, low speed is economical, whereas high speed is costly enough. Coming to thermal energy storage system, you can see that it can be classified into 3 types of sensible, latent, and thermochemical. And again, sensible 2 types, liquid and solid. And liquid can be actually using water. Coming to solid, stone and soil has to be utilized. Okay, and here in this thermal energy, latent heat also one is sensible. Second, in case of latent heat, phase change has to be taken into account, has to be considered. Solid to liquid as well as liquid to gas, and solid to liquid by melting, and liquid to gas by vapor. And coming to thermochemical, there are 2 techniques. That means under the presence of heat, okay, chemical reaction takes place, okay, or sometimes from chemical reactions heat will be generated. Mostly if you consider solar thermal applications, that means the heat is under the presence of external heat, okay, chemical reactions takes place, and using which, that means either by sorption technique or by reaction process. Again, sorption means attachment, that means adsorption. One is adsorption, that means linking, attaching or sticking onto the layer electrode surface, and absorption is completely sinking into that. Okay, the reaction, that means chemical reactions takes place based on the stoichiometry of the selected electrolyte and electrodes, and solid gas and solid liquid can be achieved. Generally, we know that in this storage method, thermal energy is stored by heating or cooling a storage medium. And in general, storage of thermal energy in the case of thermal solar power systems also. Excess power generation is used to heat salt or high temperature, and molten salt is sent to a storage tank for later use. Here, one can note that storage of thermal energy is also used in domestic storage heaters, and which contain thermally insulated clay bricks, especially for space heating applications. Low tariff electricity, that means low economical one, is used to heat the clay bricks during the night, when during the day, and then during the day, the heated bricks can be used to release the heat for living space. Okay, and disadvantages of storing heat in a medium are the temperature of a medium changes as thermal energy is extracted, which complicates delivery of the stored energy, and energy densities are relatively low. For example, if you have water at 50 degrees centigrade and stored energy is to be delivered at a temperature of 20 degrees centigrade, the initial stored energy density can be multiplied with a 4000 difference between them, which was going to give you about 0.13 megajoules per kg, where the capacity of water is taken as, one can take that heat capacity of the water as 4200 and multiplied with the difference between these two, one can attain at 0.13 megajoules per kg. The energy density is increased if a phase change in the medium is involved when the energy is stored or released. For some air conditioning system, use low tariff electricity to freeze water during the night. The ice is then used to cool the air during the day. The latent heat of fusion of ice is, we know that, around 330 kilojoules per kg. That is, 1 kg of ice is able to absorb nearly 330 kilojoules of heat. Moreover, the ice remains at a temperature of 0 degrees centigrade while it is melting, and this simplifies the energy of the stored energy. Coming to the thermal storage, we can say that it can be categorized into two classes. One is physical and chemical, as we already discussed here in this slide. Okay, and we'll move on to the next most successful proven technology, so energy thermal storage technologies. One is thermal hot water storage. Okay, you can see here, in this case, the hot water to tap. You can see power range is a 40 kilowatt to maximum 400 kilowatt. One can attain. Okay, energy range is in between. For small residential, it is 6 kilowatt to 25 kilowatt hour, and for multi-dwelling building, it is around. That means like just like an apartment kind of thing, where it can go around 320 kilowatt hours. Okay, and discharge time is greater than 1 hour. Really good. Okay, cycle life is, there is no limit of cycle life. Life duration, you can see 15 to 30 years, and reaction time some seconds, efficiency 50 to 85. Okay, you can go, we can see that one here. The physical principle involved in this one is one of the a heating device produces hot water outside or inside an insulated tank where it is stored for a shorter period of time, a couple of days also, it is maximum. The stored energy depends on the hot water temperature and on the tank volume also. The tank insulation determines the thermal losses and limits the storage period. Okay, and the fuel is used to generate hot water, generally, as we have seen in the figure. Okay, at the bottom, gas, and in the more and more produce hot water and other sources heating, oil, or applicable. For room heating, hot water between 55 degrees centigrade is generated. For sanitary hot water heating, the temperature 60 degrees and 70 degrees to avoid growing. This one can overcome this bacteria, can be eliminated. Fine, we can go to the next slide as time. And one more concept is adsorption storage systems. Coming to hot water tanks, okay, the future sizing study is required. Yes. Okay. Now we can see, coming to heat storage can be achieved as we all discussed. And coming option, the physical year of this option is in general is characterized of take up and accumulation of one material by means of a second material. Okay, you can collect and accumulate of one material by means of a second material. Ions or ions of one molecule or one material by another material. That can be called as a sorption. Okay, the aggregate state of the second material is either a solid or liquid. The accumulation of a material on a surface is called adsorption. We already discussed. In the case of the accumulation in the liquid phase, the absorption and the adsorption and the absorption are both of them are exothermal processes. The release of the material absorption, which is an endothermic process, and an adsorption is a combination of two different materials. One is adsorbent, for example, geolite, and the other one is as an adsorption heat storage is nearly free of heat loss time. After charging, the storage tank can cool down to ambient temperature, but remains constant as long as the two, both adsorbent as well as adsorbate, are kept separate. Here also this is about the adsorption technique. Here one can see that have highest storage capacity of all thermochemical ones. Okay, generally solid silica gel has a storage capacity roughly up to 4 times that of water. And coming to supercapacitor, which we already yesterday it has been covered by Dalvi sir, which was going to exhibit high power density. And coming to this adsorption flow, there are two methods. One can see in that figure. There are closed cycle adsorption system as well as open. Coming to application for heating, cooling, are designed for mobile as well as storage or stationary application. Okay, up to megawatt hours. Mobile heat storage using industrial waste heat, stationary heat storage in dishwashers, stationary heat storage in a school, in any district heating application. Basic more from country to solar. Okay, that is also one more attractive feature. And next, coming to electrical energy storage devices, both the supercapacitor and superconducting magnetic energy storage, both these two things comes under electrical energy storage technologies. A charged capacitor is a store of electrical energy, which we are already, which we know from our basics. Of the capacitor, and inductor carrying a current is a energy in case connect going to use a cryogenic engine. Both these types of energy storage have been developed nowadays, and that is complete development established technologies. Now both these two are okay. There is no intermediate thermal energy step, and so thermodynamic limitations are avoided in these cases. Consequently, have very good round trip efficiencies, especially for supercapacitor, around 95%. Electrical energy can also be stored in a rechargeable battery. This involves electrochemical reactions and storage also. Subsequent delivery as the electrical fuel cells are similar. Conception with most of the people is that it's the electrochemical process, but it was not going to. It was consume hydrogen, making you hydrogen generate. That means it is a energy generated energy. It can act as an energy generator, but it was not going to store energy. Okay, that's one of the important point to be considered. Okay, but some people was going to say that means one can store energy using fuel. Okay, the energy stored in the hydrogen can be recollected. Superconductor, sorry, using that fuel cell. Okay. Okay, coming next supercapacitor figure, one can say that the capacitor plates are formed from carbon. The next effect is the plates are separated by an electrolyte containing a mix of positive and negative ions. These polarity with electrodes polarity, and these layers are at an extremely small distance from the electrodes, approximately 0.5 meters. These two features together with high relativity to extremely high values of capacitance. Okay. Generally, the applications of these supercapacitors can be used for smoothing devices. Okay, power smoothing, and they store double layer. It is also known as electric double layer capacitors. Okay, and okay. Now coming to these future developments in this area, high porous electrodes like using graphene-like carbons or carbon nanotubes are investigated in this area to specific. Fine, they can be used in uninterruptible power supplies and safety electronics for free power backup, especially for renewable energy for smoothing voltage stacks and power boost. Okay. Coming to superconducting magnetic energy storage, they are used for they are mainly both these two capacitor and inductor are energy storing, and we already know. But both the power density is more quite when compared to the ordinary capacitor. Okay. Superconducting magnetic storage, here we know that the energy stored in the magnetic in the inductor, and what makes energy storage in inductors is a practical proposition is the superconductivity, because the resistance is reduced in case of, that's why it is known as superconducting energy storage. Is a cryogenically the entire superconducting coil is placed in a, that means generally we are going to have an inductor placed coil of that means in between which you are going to have a superconducting, that coil is made up of that superconducting material, magnetic energy storage. Superconducting coil of the inductor typically made of an alloy. It is made of an alloy of niobium and titanium and is completely immersed or bathed in liquid helium in a cryogenic area, that is cryogenic. Or in other words, we can also call it a cryostat. A DC current of approximately 100 amp circulates is allowed to flow using 20 tests. Stored energy is reduced by discharging coil to an external circuit. Okay. Here you can see the superconducting schematic diagram in slide number 17. Okay, where you can see the coil is usually made of niobium and titanium. I had discussed. Okay. Now coming to energy system, three different concepts nowadays. One can store energy from power to hydrogen, power to gas. Okay, three concepts: power to hydrogen and chemical energy can be stored. That means biological energy store, hydrogen energy storage. Okay, a way to store chemical energy and store hydrogen gas. Okay, the hydrogen gas can be both thermal energy that drives the conventional steam turbine. Definitely, the hydrogen gas can be reacted with the oxygen of a fuel cell, and using which hydrogen energy storage is an attractive, because whether in air or reacted with oxygen in a fuel cell, the only indicates it is completely environmentally friendly and there is no pollution at all. More further, we already first table that nearly 140 megajoules per kg energy density can be achieved using this hydrogen energy storage. Here, hydrogen gas can be produced by the electrolysis of water. Electrolysis can be achieved by connecting that one to a DC power supply. DC, okay, and as the advantage that it works for a wide range of applications, it makes it portable. Sources such as turbines and solar also where the voltage that is generated may vary. Most commercial production of hydrogen gas employs the method of steam reforming, where you are going to get carbon monoxide, okay, as well as hydrogen. Okay, both will be obtained simultaneously, and they can be down. And again, solar cracking is also one more technique is there. In this process, high temperature steam around 700 to 1000 degrees centigrade is used to produce hydrogen from a methane source, such as natural gas. The methane reacts with steam under a pressure of 3 to 25 bar in the presence of nickel catalyst, okay, to produce hydrogen and carbon monoxide. Generally, this is an endothermic reaction, so that heat must be supplied for the reaction to continue. Then in the second stage, at a temperature of about 360 degrees, and in the presence of a copper or iron catalyst, additional hydrogen is generated through the reaction. And in that reaction, an oxygen atom is removed from a water molecule, and the atom oxidizes CO to CO2. Because CO is more okay. This is an exothermic reaction. It has been, that is, it releases heat to the surroundings, producing hydrogen gas can result in emission of the greenhouse gas, as we can see. That carbon dioxide. When compared with internal combustion engines using petroleum vehicles, then using hydrogen as a fuel produce fewer gas emissions when compared to counterparts. Small amount of hydrogen can be stored in pressurized vessels up to 100 to 300 bar, liquefied at 20 temperature. Alternative, one can and store for very large amounts of hydrogen. If you want to store amounts of hydrogen, the gas is stored salt with a volume of up to 5 into 10 power 5 meter cube, and at a pressure of 200 bar. This corresponds to an energy storage capacity. Convert that one into joules per capacity, approximately 360 gigajoules. Okay. Now, we can see that this slide number 19 about power to gas is a current concept, present day recent most concept. People are investigating on that one. That means even in Kakinada also, here we have power to ammonia. One concept is there. Okay, power to ammonia. Just like that, in power to, that means electrical energy is by electrolyzing water to produce hydrogen and oxygen. Okay. Having only 2 minutes of time. Is it okay, sir? Dilip? Dilip?
Yes, Anil.
Is it okay? Shall I have to continue? I'm having only 2 minutes of time.
Yeah. You can conclude, but conclude this because time conclude. Deliver the summary of the talk.
Okay, sir. Here we can say that means here solutions are available to increase system security. That means for the overall national level energy security, but there are so of specifications that they are difficult to compare. Okay, you can see that in this slide. We can see I am directly jumping to the application part, okay, where you can hear slide number 55 there. Okay, general applications, series in services in bulk energy mode. Okay, a bulk energy, that means energy store applications. A general application means regular one, that is services in bulk energy like.
Doctor, if you want, you can continue for 5 minutes also. No problem. This because it has to be concluded, na.
Okay.
We stop at 9 o'clock. You can
Okay, sir.
continue
Then
for
no
5
problem.
minutes. Yes.
Okay.
It's a meaningful conclusion must be there.
Yes, yes.
Yeah. Welcome.
Okay. Although that means many solutions are available, increases different in specification. Very available ES systems. No single storage system meets all the requirements for an ideal ES. Being mature, having a long life, high density, and high efficiency. Each electrical energy storage system or energy storage system has a suitable application. For example, PHS, that means, for example, pump storage, compressed air energy storage, large scale batteries, fuel cells, solar fuels, thermal energy storage, all are suitable for energy management applications. Coming to flywheels, batteries, capacitors, supercapacitors are more suitable for quality, where batteries, flow batteries, fuel cells, metal airs are the power. Coming to the pumped hydro storage and lead acid batteries, typically mature, that means everything completely available. That technology is completely available. And compare energy storage, nickel, cadmium, sodium, lithium, magnetic energy storage, flywheel, supercapacitor, and thermal energy system and high temperature thermal energy system, all are and commercially available. This is coming to fuel cell, metal air battery, solar fuel, and compressed air energy are under developments. Okay, some chemical energy storage are also under development nowadays. Okay, the capital cost of this compressed air energy storage, metal air battery, pumped hydro storage, thermal energy storage, and chemical energy storage are lower than other energy storage systems. Storage system has the cost among the developed. Okay, that is technologies. And metal, the cheapest among currently available electrical energy storage systems. Now, coming to the cycle efficiencies, superkinetic energy, because mostly stability. Okay, flywheel, capacitor, supercapacitor, as well as power hydrogen, pumped hydro storage, compressed air energy storage, batteries, flow batteries, they are high with cycle efficiencies which are above 60%. Fuel cell, within fuel cell, okay, we can say the direct methanol, fuel cell, metal air, solar fuel, thermal energy storage systems, and chemical energy storage systems have a low efficiency, mainly due to large losses, because the losses are more. There is an additional research. Okay, conversion of one form of, okay, the size of this energy is based on electrical technologies such as superconducting magnetic energy storage and capacity superconducting real high, and thermal based electrical storage system, compressed air energy storage, flywheel, and low temperature storage, energy storage, and high temperature storage, they have long life cycle. Thus, it is a complex mixture of different energy storage technologies along with their pros and cons. Therefore, the cycle abilities of batteries, flow batteries, and fuels are not as high as the other which we have seen here, okay, due to chemical deterioration, because as the life due to aging effect, okay, chemical deterioration takes place with the operating time as we are going to operate, and metal air battery has the lowest lifetime, at least as of now. Okay, thus I can that each and every that means one more important point is that pumped hydro storage, compressed air energy storage, batteries, low batteries, fuel cells, and SMEs, that means superconducting magnetic energy storage, are considered to have some effects on the environment due to one or more of the fossil fuel combustion, strong magnetic field, landscape damage, fuels. New concept that has been arriving. So new services, new have been self-employment kind of things are also been started up in other countries, in especially related to fuels. Okay, and energy storage service, T-cable services. The energy storage services are started. Okay, the private people for grid maintenance. Okay, even for micro like that. Okay, as it has been come up as a service last year 2024. Okay, and however, like this should be before we are going to consider one a particular application. Okay. Here further we can say that the development of storage techniques requires the improvement and optimization of power electronics. Okay, and it is the agenda of this FDP program also. Okay, power often vice versa, and the rate of penetration of renewable and different, especially decentralized ones, and the and overall infrastructure, energy cost, complete systems like storage, associated transformation of electricity, power electronics will lead to the optimization techniques, efficiency, stability, maintenance, social, environment. It is important to assess the national interest also for compressed gas storage techniques, okay, coming up, and investment in research and development on the possibility of combining several storage methods with a renewable energy resource will lead to the optimization of the overall efficiency of the system and the reduction of greenhouse gas created by the conventional gas burning based power plants. Assessing, okay, and increase the rate of penetration of renewable hydrogen based electrolyzer fuel cell system, a constant made. If you are having, and can also conclude that finally applications, advantages, applications of applications for grid operations and utilities in arbitrary and peaking can be achieved. Frequency for both spin and non-spin can be achieved. Voltage support can be achieved. Start, okay, using this technologies. Transmission distribution deferral can be, and transmission congestion relief can be attained, and time of use bill can be managed. Okay, both at domestic as at commercial end. Demand charge reduction can be attained. uninterruptible power system can also be attained by making use of this. That means this is the final applications which are useful development of renewable energy in the coming decades. Okay, without energy storage technologies, renewable energies, and that means development of renewable higher pace without the development of energy storage technologies. That both hand in hand. Okay, development of both technology depend on of energy storage technology. Okay. Both will just go hand in hand, and both are related. The development of both these two are interrelated, and overall development achieved by the development of both, and of appropriate energy storage choice for a particular energy, okay, is the ultimate solution for future development of renewable energy sources into microgrid of even DC microgrids also.
Thank you, Anil. Thank you very much. Just to covering all the energy, renewable energy systems. We are really excited, but you have prepared a lot. Is appreciated well. We could not able to give you time because it's late
If
night.
any doubts, I'm
Yeah, you
open
can.
to-
Yeah, you all the participants, dear faculty part. If you have any doubts on renewable energy resources, he is an expert in our. He stays in JNTUK in Institute of Science and Technology only. You can him, and he had a good exposure. He has visited the renewable resources and thank you, Anil. Thank you.
Really thankful for giving me this opportunity to.
Dr. Anil. Dear faculty, can anyone any it's time up? You have waited. Thank you for your successful and patient FDP. We have successfully completed a second session, and you the tomorrow. Take care. To participation, and with which I am concluding that today's FDP sessions. Thank you, dear faculty friends. Thank you. Good night.
Thank you.
Please, one.
Hello.
Yeah, participate. Can everyone turn on your videos?
Okay.
1 minute. Just stay for 1 minute. Yeah, thank you very much. 1 minute. Let me take the photograph.